Yeah, let's
Yeah.
start.
Oh,
Uh,
so
so I'll
hi
start now.
everyone.
Yeah,
Yeah. Hi everyone. This is Sabir. Uh, uh, I'm your host today for the workshop, and we are gonna do this workshop on autonomous vehicle. So the main focus of our workshop today is autonomous vehicle simulations. And particularly, we are going to do autonomous vehicle simulation using the CARLA software. So before today's workshop, with Dr. Karimuddin's help, so we try to share uh, the software installation process. We recorded a video and we shared the recording with Dr. Karimuddini. So I hope that you all went through through the recording and you are able to install the Carla software successfully. So today's workshop has actually three parts. So as you know from the agenda, so we actually revised the agenda a little bit. Um, so I can let me see. Oh, Dr. Chaudhary is sharing, so I'll do that later. So just a quick heads up. We made a little revision to the agenda. So from 9:30 to 10, we are going to hear from CR2C2's Associate Director from Clemson University, Dr. Mashurani Chaudhary. And Dr. Chaudhary is going to talk about autonomous vehicle fundamentals. And following his talk, we are going to start the hands-on training on the Carla software. And that's going to be from 10 o'clock till 12:30. Uh, and then we're going to have a lunch break for 1.5 hours. And we're going to start back at 2 o'clock. And in that afternoon session, we're going to have a problem for you guys to solve. So you'll have about an hour from 2 o'clock to 3 o'clock to solve the problem. And then from 3 to 3:30, we are going to join back and we're going to discuss and review your solutions. And we're going to discuss if you faced any challenges or how we can resolve those. So without further ado, let me give the floor to Dr. Mashurani Chaudhary. Sir, please feel free to go
thank
ahead.
you. Thank you all. Thank you for participating. I hope it will be a useful workshop for you. We are just not covering the fundamentals, the theory, but we're also covering hands-on exercises. So after we share how you can work with the simulation software CARLA for autonomous vehicle simulation, autonomous and connected vehicle simulation, then we'll also go through an example problem, and at the end, you'll be able to do a problem hands-on. So, and we want every one of you to complete that assignment. So your learning will be optimized for today because you're spending a whole day, almost whole day today. So we want you to get the best out of the workshop. So I'm Ronnie Chaudhary. I'm the co-associate director for CR2C2, and I work closely with Ali. It's my pleasure to talk about autonomous vehicle and how you can simulate in a CARLA environment, which is very popular. It was developed with a sponsorship from USDOT, and I see in the industry and academia, a lot of people are inclined to use CARLA for their autonomous vehicle simulation. So just a brief video on autonomous vehicle. You can see a autonomous vehicle, a driverless autonomous vehicle is moving. And those of you who are at NCNT, you have a test track with autonomous vehicles, so you have experienced that all the time. But this came from the Tesla Motor Company. So the autonomous vehicle is running. And you can see the inside also in the video of the vehicle. There's no drivers present, which is, we'll talk shortly. This level 5, right? So there's no drivers presence. It can just go autonomously from one location to another location without any assistance. So there are several companies who are making autonomous cars. So and depends on like what level of autonomy we are talking about. From level 3 to level 4, you will see a lot of companies are have their vehicles tested, and some of them are operational in the real world. So I was recently in Atlanta, so I took this autonomous uh, car taxi. So from going to one point to another point. So it was a great experience. And a lot of the cities, the bigger cities, you'll see that you have these cars driving through the roads. All right, so I will go to the next slide. So to give you a brief history of autonomous vehicles. So it started a long time back in 1948 with the modern cruise control. See, so as you can see, it was a long, long time ago. And that was actually the foundation for autonomy. And then there are different companies invested uh, resources in building more autonomous system from Mercedes-Benz to BMW. They invest a lot of money to have the autonomy in their cars, in their vehicles. In the US, also, there are a lot of companies have been investing from General Motors to Ford in transitioning to autonomous, at least semi-autonomous, and then ultimately autonomous vehicles. And you can see today we have fully autonomous cars, but with driver backup. So it's a regulation in many states that you have to have a driver, licensed driver in the car to take over the system if there is anything wrong or if the situation calls for it. And so that's we have autonomous cars, but now the broad adoption will happen soon. And you can see the projection. It is coming from the IEEE. IEEE is projecting that 2032, half of the new cars will be autonomous. That's a huge thing, right? So I see that from 20 late 20 maybe late 2030 you'll see that a lot of the cars on the roads are autonomous cars. So we should be prepared for it. And the research that are being done at CR2C2 will actually provide a lot of input on how to deploy these autonomous cars safely and securely. So this is the list of autonomous cars available today, but it's not an exhaustive list. There are other companies too who are building autonomous cars. So here we have the Waymo, which you'll see in the many taxi fleets. Like in Atlanta, you'll see the Waymo services. Many large cities have Waymo services. General Motors has built autonomous cars. Uber already has autonomous cars. They're testing in many locations. So Tesla, right now you can buy an autonomous car and autonomous services. We ride. So a lot of companies you see they are already working on it. So as a researcher or academics, we want to make sure that we contribute to the safety of autonomous cars and they run most efficiently on our roadway network. So some of you may have seen this level of autonomy. This is the SAE, Society of Automotive Engineers standard, level 0 on the top row. You'll see this how the driver, in terms of drivers, what is the function from no automation to full automation. You see the drivers is shaded out. So it's more and more the robot is taking over the driving task. And on the lower row, you have the driver behavior. So from the full control of the vehicle, full driving responsibilities, to partially going less and less driver functions. And at the level 5, you'll see always driverless. So let's look at level 1, speed or steering support. Level 2, steering and speed and steering support. And level 3, eyes off in some situations. And level 4, which is we see a lot of the vehicles in level 4 conditions today. driverless in fair conditions. So when needed, the drivers should take control. But when the conditions outside are favorable, then the automation will drive the vehicle. And level 5, which is coming, as you saw, that in 2032, half of the cars will be autonomous. So it's always driverless. That's where we are going towards. So how does the autonomy stack in an autonomous car work? So here are the main functions, main categories. So we have sensors. We have external sensors and we have internal sensors. External sensors looking at the outside, perceiving the outside, and there are some sensors that are actually measuring vehicle functions inside. Now, we have this perception module in the autonomous car based on the input from the external and internal sensors, sometimes a fusion of different sensors. It's perceiving what is outside, whether it's a road marking, whatever road marking it is, whatever sign it is. So it's classifying the type of traffic sign, and also it's detecting object. So if there is suddenly an object in front of the vehicle, it will detect. If there's a pedestrian in front of the vehicle, it must detect that, right? So, and then we need to predict. So this autonomy stack will predict. So in time t+1. So I know what's there now with my sensors, but we have to have a prediction module so we can predict that if I see the pedestrian at this point now, what will happen in 1 second, where the pedestrian will be, where the another car will be. So we have a prediction module, and that module predicts and also tracks the object that it predicted that the pedestrian will be there. But we also verify with tracking that that's what's happening, and we correct course based on what's happening in the future scenario. And then we have planning. So we'll talk about it in more detail, from route planning to trajectory planning to motion planning. And then the control. So the drive-by-wire system is used to electronically control your brakes, your steering wheels, accelerators. So in robotics, we always say that that we have some main components, right? So this is sense, think, act, right? So in robots, we said that we sense, think, and then act. So for autonomous vehicle, it just similar functions. If you expand it, it's sensing with sensor, then perceiving, and then predicting, then planning, and then controlling, as I showed in the diagram or the figure up. So the two types of sensors, I'm just showing some of them. It's not as exhaustive because different companies will have a different area of sensors. So the type of sensors Tesla have, it may not be similar to what Mercedes-Benz have. So it might differ based on what algorithms they use, whatever sensors they need. So exteroceptive sensors or perioceptive sensors, you can see that the LiDAR, radar, camera, they are looking at the outside, they're measuring the outside, where proprioceptive sensors, they're measuring the inside, like GNSS, IMU or internal measurement unit, wheel odometry. So sometimes a combination of this sensor data, the autonomous vehicle makes a decision what to do next. So about those external sensors, so here's the camera. So it detects roadway signs, signals, markings. So because it's like our eyes, so we see as a driver, we see with our eyes what's going on. So it is replacing our eyes. And then you can see that it's marking different objects and then determining what is that object. So LiDAR, it create the 3D point cloud. So it for identifying obstacles and also the free space. So some autonomous vehicles do not have LiDAR, but then they have to rely on other types of sensors. And also determine the edge of the road so the autonomous vehicle can go safely with the alignment it's driving towards. So radar is a very good tool in different types of weather conditions. In adverse weather conditions, the video cameras could be may not function as needed. So then the radar can use to measure objects where they are, how far they are, and also they can be used for tracking. So the vehicles in front of an autonomous car or another autonomous car in front of an autonomous subject autonomous car. So this is an important item, the sensor fusion and redundancy. I see that we can do a lot of research in this area, how fusing sensor data, we can optimize autonomous vehicle operation, safety and security. For example, we are doing a project on GNSS and GNSS or GPS. So we are seeing that when the GPS is compromised, so we can utilize the different other sensors in an autonomous car for camera and radar and internal sensors. So we can utilize those external and internal sensors to move the autonomous vehicle in a GPS denied environment. So I see a lot of opportunities for research on how we can utilize these different sensors, and under certain situations we can use this sensor fusion to make sure the autonomous vehicles are driving safely and securely. And also sometimes you need redundancy for safety. If one sensor fails, the other sensor should be able to take over the sensing task. So the real perception can happen. So SLAM is to locate the autonomous car where they are in relation to the external world, showing autonomous vehicle moving, and it is using SLAM for location. So perception, I mentioned this first task after you get the data from the sensor. So we are trying to answer the question, what's around me? Whether it's with the video, you're looking at what it is inside, in front of you or surrounding you. Is a truck or a vehicle or pedestrian? Prediction is where we try to predict what will happen in time t+1. We can, as you can see, the subject autonomous, it's a truck, is moving, and it is looking at the camera, the vehicles around it. It's detecting through camera, it's detecting through radar, and also it uses historical data to verify some of the things that it's seeing in front of it, and most importantly, to predict. So if I'm at this situation at time t, what will happen within a couple of milliseconds? You can see that it's just the vehicles around it. It's the subject truck is predicting so that it can move on a safe trajectory. Now planning, three categories. Route planning, like you're using a map to go from, say, one point to another point. And motion planning, what maneuver should the autonomous vehicle take next? For example, will it march, change lane, yell, stop? And trajectory planning is in a more microscopic level. It is what to do in a very short time, like in a millisecond level. So does it have to move the autonomous vehicle have to move the steering? Does it have to press the pedal? So the difference between motion and trajectory is the amount of time. So trajectory planning happens in a much more microscopic level than motion planning. So this is just expanding on the route planning. The reason we are covering these fundamentals because it will be needed for the workshop we do later for your using the simulations. We will cover some of the items you are seeing now. So it determines the global path. As I mentioned earlier, it operates at within a city level or between. So I'm going from Winston-Salem to Greensboro, so it operates at regional scale as well. It uses maps, topology, traffic rules, and constraints. So in terms of time, that's the difference between them. Uh, Computed once and not very frequently unless the conditions change. So the output is a sequence of roads, lanes, and waypoints. So motion planning, we also call it tactical or behavioral planning. So it determines how the vehicle should move locally to safely and efficiently follow the route that we need to move on as we determined earlier through route planning while interacting with the external environment. It operates at a local scale, like so it's seconds ahead and it looks at the nearby surroundings. It considers other vehicles, obstacles, objects, road geometry. So and it balances between safety, comfort, and the rule of the law of the roads and efficiency. And it's updates. It's like within a second or so on in second level, uh, based on the external environment, the changes in the external environment. Trajectory planning computes a very precise time index path of the that the vehicle will follow. So which includes the position, speed, and acceleration. So as I mentioned earlier, it operates at a very high frequency in millisecond level. So it produces a smooth drivable path, and also it has to consider the vehicle dynamics and physical limits. So you cannot uh, implement an action that will violate the vehicle capacity and the physical limits of the environment. And it is directly feeds to the control system. So the braking, the steering that are happening and that are instruction from the control system is happening because of the trajectory output from the trajectory planning. So this is the final level control. So there are two types of control, as we have learned in driver behavior modeling. We have a longitudinal control and lateral control. So when a vehicle drives along a path, so it goes forward or it changes lane, goes sideways. So this is like you can think that car following theory, it's following the car following theory, and lateral control, it is following the lane changing theories. So what it does in the longitudinal control, it maintains a desired speed and also the headway between the autonomous cars and the cars surrounding the autonomous car. And it can handle like build ups and downs on the road as well as curvature. So a typical type of controller for longitudinal control is a PID style controller, spacing control, and model predictive control, which has been around for a long time. Uh, so these are the three mostly used types of controller model, but there are others as well, but these are used frequently. So now the lane changing or lateral control follow a lane center line path, and then also it changes lane when needed, or goes sideways when needed. So I'm on the rightmost lane if I want to go to the leftmost lane. So what actions I need to do? So the controller implements those actions. So some common types of controller families for lateral control: geometric pure pursuit style, Stanley style, and model predictive control style, which is also used in longitudinal control. So this is a very favorite subject of mine. I always say that we have to test it. So you can test with simulation, but also you need to test in the real world. So C2 has a great facility for in Greensboro to test the autonomous and connected cars. So sometimes you can combine the simulation with the real life. So for some type of autonomous vehicle in the loop type simulation, we also do it here a lot. So when we test the security measure, so we have an autonomous car, we have our own autonomous car, we are moving the autonomous car, and we have an ghost car in front of the autonomous car. So, and we see that when the autonomous car is attacked, what happens with the car in front, a virtual car in front of it, and versus there is no attack, what happens to the autonomous car. So in the loop simulation is a great tool to do research, and definitely nothing compares with the real world testing. So that's so we can use this we use these three tools to update our autonomous vehicle design and adapt to changes what's happening based on our research and based on the knowledge we gain throughout developing the autonomous vehicle. And we always try to improve, right? Our main goal is to improve safety. And then definitely we have to be operationally efficient and the system has to be secure. So there's some safety standards that we should be aware of. So ISO 26262 is for functional safety. It has so it's make sure that the functional safety life cycle for minimizing risk from malfunctioning, and so it is based on a risk-based modeling. So if you are developing any company developing autonomous car, so they must follow the standards that are there, and there is an extension of this ISO 26262 for safety of the intended functionality. So how, what are the limitations of if there's an unexpected condition, how the driver assistance systems and the automation will function? And there's an, so these are extended of the existing standard, and there's an emerging standard for AI in autonomous cars. So how the AI ecosystem will work. So it's related to covering the AI specific hazards and assurance. So if AI system is compromised, how the system will function, the autonomous system will function. Now, these are cybersecurity related standards. The three standards, the ISO SAE 21434. So what you need to do to ensure that your system is cyber secure. And there's the next one with the regulation, how you manage the cybersecurity system. You will hear this term, cybersecurity management system. So that for original equipment manufacturers. So all new vehicles must adhere to this standard, cybersecurity management. And then the software update is a major issue for cybersecurity. As you have seen, like when you try to, you have to update your phone software from time to time, but that might create an attack surface when you're updating software for autonomous cars uh, every few weeks or so. So we want to make sure that how we manage the software updates in autonomous car, because we have seen through our research that that's a major vulnerability for connected and autonomous cars. So we have to also consider the ethical problems, ethical issues as a autonomous vehicle engineer. So some of you may have heard about the trolley problem. So if you're a driver of a runway trolley about to kill 5 people, so unless you switch the track, so if you do not switch the track, one person will die. If you switch it, if you don't switch it, 5 people will die. If you switch, 1 people will die. So you can think also an autonomous car moving, and they can so it's about to crash. So there's two consideration that the autonomous car can try to protect the driver or the occupants of the autonomous car, or it can harm the pedestrians around the autonomous car. There are only two options, right? So in that situation, what the robot will do in the car. So those are the ethical considerations we need to consider. So as an autonomous connected vehicle engineer, so I I urge you to look at those ethical problems too, so that our system is safe, secure, and ethical. I think right now we'll go to the training. Unless you have any questions, so we'll move to the training. We'll use CARLA, and you have instructions from us how to download it. Has anyone in the audience not downloaded CARLA yet? So then you can do it now because we were having some hard time initially to follow the manual to download. Then we found an easy way to actually download the software. So and it worked very well.
So I put in chat box the video that previously shared with us. So it is now in chat box.
Okay. Any questions before we move to the exercise training?
Very interesting overview of a lot of topics. Thank you so much.
Yeah, because thank you, Ali. Some of the information I provided, it will be used in the training later. So that was just introducing the concepts. Thank you. So if there's no question, Sabir, will you take over the
Yeah,
next one?
sure. Thank you, Dr. Choudhury,
Uh,
for your
just
presentation. Yeah,
I apologize. Just one quick thing. So Dr. Sabir Shalek has a very dynamic background. So he actually a mechanical engineer. He started as a mechanical engineer. He did bachelor's and he was doing master's in mechanical engineering at Clemson University. Then he did. I knew about him. He's a star student at Clemson. So I hired him to work for our center in autonomous and connected vehicles. So, and he worked on autonomous vehicles for a long time. We had a project from the U.S. Army on autonomy on the wild, so in unstructured environment. So he had a couple of years of experience at doing fantastic research on that project, and now he's working on safety and cybersecurity of autonomous cars. So we have a great trainer here. So now Dr. Sabbir Shalek is a senior engineer supporting CR2C2. Now I'll just go to Dr. Sabir Shalek. You are in a good hand. Thank you.
thank you, sir. Thank you for the kind introduction and your talk on the autonomous vehicle fundamentals, so which will be very useful for our hands-on training today. And a lot of things that Dr. Choudhury covered, we are going to try to see how we can do those things on CARLA. So starting from different types of sensors, how we can set those up in CARLA, how we can collect data from them, how we can render those data to a window where we can actually see what the sensors are capturing, right? While the vehicle is moving, how to drive a vehicle autonomously, how to control it. So with different types of controllers, like Dr. Choudhury mentioned about the longitudinal controller, lateral controller, we'll try to do as much as our time permits. So that's why I wanted to share with you the CARLA installation recording before we joined this workshop today. So I hope you had the chance to look at the recording because it takes some time to be able to install CARLA on your local machine. And you also need a computer with, I'd say, good or fair configurations in terms of your graphics processing unit, GPU, RAM, and also the disk space left on your computer. So I hope that you had the chance to go through the recording and install it on your machine. So what we are going to do today is we are going to assume that you were able to successfully install the CARLA software, the server part of it, and we're going to show you how to set up the client side of it, and that will communicate with the actual server of CARLA, and then how we can do different sort of operations from the client side by running different commands. And this workshop is going to primarily focus on the Python programming for CARLA. Now, just to keep you informed, so in CARLA, you can code either with C++ or you can do with Python because Python is very popular these days. So we are going to use Python-based CARLA training today. Uh, Now let me share my screen and make sure that we are all on the same page regarding uh, the installation and everything. I see that's recording. Mhm. Sure. All right. I hope you can see my screen. Let me know if you don't see the screen. Uh, all right. So we're gonna start. Okay, let me open a new window. That would be helpful. All right. Okay. So first things first, we are gonna go to the CARLA's official website, which is carla.org, O-R-G. So if we go there, we see that the latest version of CARLA available is 0.9.16, but there's another release 0.10, which is based on the Unreal Engine 5.5. The version we're going to use is 0.9.16, the most latest, most stable version to date, and it is based on Unreal Engine 4. Now, okay, let me go to, so once you click Get CARLA 0.9.16, it takes you to this other web page where you basically have everything you need to know about CARLA. So this is the CARLA's official documentation for 0.9.16. As you can see, if you click on it, uh, it opens up the GitHub page of the CARLA software, from where you can also download the tarball file, or you can read about CARLA. You can get the source code if you want, if you need, and also the different information that you'll need to know about this. Now, going back to the previous page where we had the documentation. So this web page is going to be your primary source of resources regarding CARLA. So anything you need to know about CARLA, if you are trying some new things after this workshop with CARLA, you are trying to communicate, make CARLA communicate with another software that you typically use, could be Robot Operating System, ROS, could be AutoWire, could be any communication type software where you simulate the communication between vehicles, uh, uh, any difference, or any physics engine, for example, Chrono or something else. So CARLA has a way to interface with the different, many different types of softwares that we typically use for autonomous vehicles simulation, starting from physics engine all the way to vehicle or vehicle to infrastructure level communications. If you want to control the traffic signals in CARLA with some traffic simulation software, you can also do that. So CARLA has ways to do those. But that's not the focus of our tutorial today. So our tutorial today, or workshop today, will primarily focus on how to use CARLA, how to set up an autonomous vehicle in CARLA, how to set up the sensors, how to get data from them, uh, how to drive it autonomously on the road, how to change maps, populate the driving environment with different cars, different weather conditions, all those things. So we are primarily going to focus on the capabilities of CARLA today. And once you have that background, you can always look through this documentation to figure out if you want to communicate with some other software, or make CARLA communicate with some other software that you are using. You can always get it from the CARLA documentation, as long as it is, the facility is available. So you can see that in this documentation page, if I scroll down, as I was mentioning, so in the CARLA ecosystem, you can talk to ANSYS, which is a physics type simulation software. You can also talk to the AWS, Amazon Web Services. You can talk to Parsim, another simulation software. You can talk to Chrono, which is basically a physics engine. I would not say very much similar to Unreal Engine, but it's also a physics engine that can simulate the world physics when you are working with some simulation. You can talk to MathWorks and so many other different software you can talk to from CARLA. Now, let us begin with um, the installation process. Just two comments on the installation. So in the recording, I showed you how to install CARLA on your computer based on this web page. So that procedure follows the quick installation process. So in the quick installation process, you have everything that is offered by CARLA, right? So, but if you want to create your own navigation map, So for example, if you want to create your own world in CARLA, or if you want to create your own autonomous vehicle in CARLA, building up all the different components in the vehicle, not uh, using the ones that are already being offered by CARLA, then you will need the developer version of CARLA, and that takes up a lot of time. But there are tutorials on YouTube, there are blog posts that you can follow through to be able to install the CARLA developer mode. And once you have the CARLA developer mode, although it is not needed for our workshop today. But once you have the developer mode, you can actually do everything that you want to do with CARLA, to be honest. You can create your own world inside CARLA with your the physics and everything. You can create the traffic lights, how to shape them. You can change the geometry of the road and everything. You can define all those things by yourself with the developer mode. But that takes up a lot of time, just to give you a heads up, and you'd have to set up if you're using it on Windows, it's going to be quite a challenge to be able to install the developer mode. But uh, you have to fix a lot of bugs maybe, and fix a lot of compatibility issues with different software components. So that's another thing, and we're not going to talk about that today. So, but the version that I installed in the Zoom recording, and the one that Dr. Karimuddin just shared in the chat, um, that one is good enough for CARLA quick installation. And with that, you are going to be able to simulate uh, anything that you want to do using the built-in capabilities of CARLA that is offered today with this version. All right, so let's now start with the client-side setup first. So I hope you have prior experience with Python, because this is going to be very useful today for our CARLA workshop. So what we are going to do is you can actually do the coding from any Python IDE, but it is highly recommended that you use Anaconda and Jupyter Notebook. Now, in case you are not familiar with Anaconda or Jupyter Notebook, so what you need to do is you need to go to Anaconda. Oh, okay. I'm going to write Anaconda Python. All right. So if you go to the Python free download Anaconda, this is the Anaconda website. So from here you can download the Anaconda for free. It's an open source tool for different Python-based applications. So once you have downloaded it, what basically it does, it sets up different Anaconda components, and one of those components is the Anaconda prompt. So I have already installed it on my computer. If you don't have Anaconda installed on your computer, feel free to install it right now. If not, if you have any other Python IDE installed on your computer, that should be perfectly fine to work with CARLA as well. So no worries there, but I'm more comfortable with Anaconda, so that's what I'm gonna use today. So if I open up the Anaconda prompt, so you basically see this shell where we can use command line interface type commands, right? And from here we're gonna launch our Jupyter Notebook. We're gonna launch the CARLA application and so on. But before we go into that, let me go back to the CARLA root folder. So this is my CARLA root folder where I installed CARLA. So if you are able to successfully install CARLA, this is what you would have on your side too. Once you go inside this CARLA root folder, you see this application file, which is called CARLA UE4.exe. Now you can just double click on the application to open this. So that's what I'm gonna do. And this will basically set up the server side of CARLA. So once you double click on it, it opens up a window, and you might have to wait 1 or 2 minutes before the window gets loaded with the CARLA world environment. And the time depends on the processing power of your computer. So mine is still loading. I opened it, but it's still showing black screen. Oh, it's just loaded. So here it is. So you can see that this is the environment of CARLA. and this is the view of the world that we have loaded in CARLA by default. And you can actually use your mouse and your keyboard to navigate through this world. So if you want to change the view, the orientation view, you want to look up, look down, look right or left. So you can do that using your mouse, as you can see. So you'll have to press and hold your left click button, and then you'll have to move it around to be able to move the spectator view of this window. And then if you want to go to a particular location, if you want to navigate through this window, the keys that you will use are Q, W, E, A, S, D. So W takes you forward, S takes you backward, A takes you towards the left, and D takes you towards the right. It's very much similar to when you're playing a game on the computer, right? And if you want to go up in the wind, so you press Q. Oh, sorry, Q takes you downward. My mistake. And then if you want to go up, then you press E. So E takes you up, right? So and if you use your mouse and keyboard together, you can actually change the orientation of your spectator view and at the same time move through this world. So as you can see, the world looks very realistic here. You have all these different lanes, roads. You have the traffic poles. You have the traffic signal devices here. So the signals are changing from green to yellow to red. You have other traffic control devices like the street names. You have passenger cars only. You have stop signs. You have yield signs. All those things, right? And feel free to take some time to navigate through this world. It's going to be a lot of fun. You see, a food court is there too. So all those things are already set up. You have buildings, you have trees, but right now you do not have any vehicle operating on the road, right? So for that, we'll need to. It basically loads the world environment for your application from the CARLA server side. Uh, but if you want to populate this world with vehicles, with pedestrians, bicycles, fire trucks, any sort of other objects, you can always do that. So those capabilities are there. So first of all, before we start using the client side, what I'm going to do is I'm going to show you how to populate this world with vehicles, pedestrians, and so on, and also how to change the world, because there are different type of worlds in CARLA. There could be 10 to 15 different types of world that you can load, and this is just one of them. So let us open up uh, an Anaconda prompt, and let me go back to the CARLA root folder. So this is the CARLA root folder. And inside the CARLA root folder, you have this folder called Python API. So if you double click on it, you see that there are three folders: CARLA, examples, and utility. So if you go inside the examples folder, you'll see all these 32 different Python scripts already written by the CARLA developers as examples to you. And this would be a very good resource to have to be able to see how you control CARLA from a client side, right? So the scripts are fully developed, and you can run any of the scripts to be able to deploy cars, open up LiDAR, or deploy any type of sensors that you would like to. So the scripts are already there. And if you want to communicate or set up CARLA with some different other software, as we mentioned. So you see that some of the scripts also mention that. So for example, this one, manual control CarSim, manual control Chrono. So CarSim and Chrono are other third-party softwares that you can use, and you can make them talk to CARLA and kind of do a co-simulation kind of thing with CARLA and other software. Now let's try to run one of the applications and see what it does to the CARLA world. So what I'm going to do is I'm going to go to the address bar of this folder. I'm going to copy it, and then I'm going to go back to the Anaconda prompt. Now I'll try to do all the steps as slow as possible so that you can follow with me. And I would recommend that you follow through with me. You try to do whatever I'm doing on my end on your computer too. If it's not too difficult to have all the windows because you're gonna have all the different windows, the Zoom window, the Anaconda prompt and the CARLA server, the CARLA client side, the Jupyter notebook. I hope you can manage all those windows side by side. Uh, so what we are going to do is we are going to change our directory using the change directory cd command, followed by the address that we just copied to the CARLA root folder. And inside the root folder, we went to Python API and examples. So let's hit enter. So it just changed the directory to the CARLA root folder. Now what we are going to do is we're going to run Python. Oh, actually, I'm going to activate an environment. I don't think I need to activate my environment here. Let me see if I have the Python installed here. So yeah, I have a Python installed here. So I can run any Python scripts from here. So what I'm going to do is I'm going to type Python and I'm going to run one of the scripts that are already available in the examples, right? So you see that there are many different scripts, and the script that we are going to use is this one, generate traffic.py. So once we run this script, what it's going to do is it's going to essentially deploy some traffic on the world that we see on the server side, right? So what we are going to do is, I'm sorry, I'm going to open the Anaconda prompt here. What we're going to do is we're going to run the generate traffic.py. So Python generate traffic.py, and I'm going to hit enter. Okay, it's showing that no module named CARLA. So what we need to do is we need to install CARLA here. So what I'm going to do is I'm going to pip install CARLA. So this will basically use the pip command to install CARLA so that we can run that generate traffic.py application. So know that this is different from the actual CARLA installation. This is basically installing the client, setting up the client side so that you can use a client application to communicate with the server. So now that we have installed CARLA, what we are going to do is we're going to run the same command again, which was Python generate underscore traffic.py. So this is hopefully going to run the generate traffic.py. So you're going to allow this to be uh, to be able to communicate with the server. And as you can see, so the world already has spawned some vehicles, some bicycles, some motorcycles. Oh, some pedestrians are there too. And let's navigate through this world. Okay, so you can see that there are cars running through this world. They're following, of course, the traffic rules and regulations. Pedestrians are crossing the street. So the world is already populated with cars. So let's go back to here and look from here. Okay, let's see. Yeah. All right, so it generated traffic. So this is a random generation. So random number of vehicles have been generated and they have been assigned on autopilot. So they are running autonomously in the CARLA environment. And if you go inside the script, you will see that there are different argument options that you can use with generate traffic.py. You can actually set up how many numbers of different vehicles you want to deploy. You can set up how many different number of pedestrians you want to have. So all those things can be set up. But those are based on example scripts that are already written. So we are not going to talk a lot about that. Instead, we are going to see how we can create our own script, right? So that's we're gonna dig deeper than this. Now let's going back to the Anaconda prompt. So you see that it's saying that spawned 30 vehicles and 10 walkers, and press Control plus C to exit. So right now we have 30 vehicles and 10 pedestrians on our CARLA server side. I'm gonna stop this. So as soon as I hit Control C, so you see that it destroyed the 30 vehicles and it destroyed the 10 walkers that it had. So right now the world is gone post-apocalyptic again. Okay. So I'm gonna open another Python file now. So let us open Python manual controls.py. So this is another Python script already that comes already with your Python installation in the examples folder. So if I run this, okay, it says that there's an error. The error is we do not have any module named Pygame. So what we are going to do is we are going to actually set up a dedicated environment for CARLA first, and we're going to install all these different modules so that we don't go through these errors every time. Now, I already have an installed environment in my computer for CARLA, but I'm gonna share what you need to run on the command line interface to be able to set up an environment with Conda. So first of all, uh, the first command, let me just first copy and paste this so that you can, okay. And then I'm going to explain each of the commands. Let me put it on the chat. All right. So you can run the commands one by one. So what it does is already on the chat. I put it on the chat. Feel free to look it up. So what you are going to do is you are going to copy one commands at a time, and you are going to put it in your Anaconda command line interface and hit enter. So the first command, which is conda create in CARLA, it basically creates a conda environment with the latest Python version that is available to Anaconda. And then once you have set up that environment, you basically go to this conda activate CARLA. So it activates the environment. So basically right now it's showing here that we are in the base directory or base environment directory for Anaconda. But once we have created the CARLA environment, we can actually activate a particular conda environment. So for example, here because I already have the environment set up here, so I'm gonna see if I can activate it. So I'm gonna type conda activate CARLA and hit enter. So as you can see, the base has changed to CARLA now. That means we are inside the CARLA environment that we have created. And once you are inside the CARLA environment, what you should do is you should run the rest of the commands. So the first command here, Python m pip install upgrade pip, this basically upgrades the pip command of your Python uh, execution, and then the pip install CARLA makes sure that you have the client, everything that you need for the client side to be working with the CARLA server. So do run that command, and then you're going to do pip install numpy, pygame, networkx, opencv python. So these are different other library packages from Python that we will need to be able to do all the stuff that we're going to do with CARLA today. So run this command, so it's gonna install all the prerequisites for our work today. And then last but not the least, please run the conda install y notebook c conda forge. So what it's gonna do is it's gonna set up a Jupyter notebook where we can run cell by cell commands. So instead of running the entire script at a time, we're going to be able to run one cell at a time and see the effect of it on the server side. So I'm going to give you a 5 minutes break here so that you can go through all these different commands and you can set up your CARLA conda environment. But in the meantime, if you have any questions, I'm here. Feel free to just unmute yourself and ask the question. So I'm going to take a pause for 5 minutes here. We're going to start back at 10:40. Okay, I hope you had the chance to run the commands. So if you were successful in running the commands, it should set up uh, the CARLA environment with Conda in the correct way. And you should have all the necessary packages that we will need today to be able to communicate with the CARLA server. So let me see. Okay, so let us start with the fun part now. So now that we have the CARLA environment set up, what we are going to do is we're going to open up our Jupyter notebook by typing Jupyter notebook. So if you were able to run the commands, the last command that I posted on the chat, that should be able to set up your Jupyter notebook. So just type Jupyter notebook and hit enter. All right. So as you can see on my browser, it's opening up this directory where I have okay. So it because I was um inside the folder Python API examples, so it took me to that directory directly. That's not where I want to code. So what I'm gonna do is I'm gonna go back to my Anaconda prompt. And first of all, I'm going to close this window here. And then I'm going to go back to my Anaconda prompt window and hit Control C a couple of times. Just hit it a couple of times. So it's gonna close the Jupyter notebook. And then I'm going to change my directory. I want you to create a directory on your desktop. So just go to your desktop and in the desktop create a. So I'm going to go inside my PC. C, and then users. For some reason, that's how I have to go to my desktop, not directly clicking on desktop. Okay, so this is my desktop. As you can see, this is my desktop inside my in my profile here on this computer. So I recommend you to create a folder, a new folder on your desktop. You can name it as you wish. So I named this folder CARLA Trials. So create a new folder like this, CARLA Trials, and go inside that folder, and then copy this entire address of this new folder that you created from the address bar. And then in the Anaconda prompt, change your directory to that folder by typing cd followed by the address that you just copied, and then hit enter. All right, so it took me to inside that folder. So now if I type the same command which I used before, the Jupyter notebook, right? And then hit enter, what it's gonna do is gonna open up a Jupyter notebook in this particular directory. That's where I want all my CARLA files that I'm doing trial and error with to stay at one place so that I can later go back to those files and check if I want to check something. All right, so here, as you can see, it opened up uh, this window on my web browser where I already have two scripts written before as I was trying to work with CARLA. And then what I'm gonna do is I'm gonna create a new file here where I'm gonna work with you guys on the CARLA tutorial today. So what I'm gonna do is I'm gonna hit new and then do a new Python 3 IP kernel. So if you click that, you see that it automatically opens up a new window, and a new cell comes up where you can actually write anything you want to write. But basically, we're going to write codes in Python here. And if you go up here, you see currently it's untitled. So what I'm going to do is I'm going to name it CARLA Workshop for today. Uh, so it changes the name of the script here. So this is not a Python file, so you cannot run this with a Python IDE directly, but this is an IP kernel file that you have to run with a notebook, like this Jupyter notebook here. But the great thing is that you can actually now just run or type one single or multiple lines of codes, and then you can just execute it directly, and we would see the reflection on the world here on CARLA. So on the left side, I have the CARLA server open. On the right side here, I have my Jupyter notebook open. And on the right bottom, I have the command prompt on Anaconda open here. Now, while we are working on this, I will actually, I won't need this Anaconda prompt much. So I'm gonna minimize the window so that you can see whatever I'm typing here on the Jupyter Notebook. Now, if you already have installed the Pygame, NumPy, the OpenCV, Python, uh, you should be able, and the CARLA, of course, you should be able to import CARLA here. So I'm gonna write import CARLA and then hit enter. Actually, Shift Enter is going to run the cell. So Shift Enter. So once you press Shift Enter, so it executes the command that you just wrote in that inside that cell. So right now we have imported CARLA, so we can now communicate with the server side. So this is my server side where I'm hovering my mouse, and this is where I'm gonna set up my client side. So I'm gonna type a command that set up a CARLA client. And the way you set up the client is I'm going to assign it to a variable. So you have, because you already imported this package CARLA, and these have a lot of different methods that you can use. And one of those methods is essentially the client method. So we're going to type CARLA client, CARLA.client, and then inside CARLA.client, you can actually have two arguments. So say, for example, X and Y. So the first argument X is basically for the server. So right now my server is set up on the same computer where I'm gonna run my client. So the server is essentially the local host here. So I'm gonna type local host. But if you have the CARLA running on a different machine, so for example, you can set up the CARLA server on a network computer, like in the cluster of your university. You can set up the CARLA server, and then from your local machine, from your lab computer or your laptop, you can actually set up the client side and communicate with the server that is running in the cluster, right? And that gives you a lot of flexibility, because when you are running the server and client on the same computer as I'm going to do today, sometime you are going to see some jittering here, that the screen is uh, jittering from time to time, right? And you're going to see that sometimes some of the windows are coming as black windows. Sometimes some windows are coming as just nothing is loaded there. So that's because we are using the same GPU, the same machine to run the server and client at the same time. But if you want to avoid that, you can always set up the server on cluster computer, and you can put the IP address here. And as long as you are connected to that server, you can set up the client on the connected laptop or other desktop that you're using. All right, so that's it for the first argument. The second argument is basically the port number where CARLA is running. So by default, CARLA runs on port number 2000 and 2001. So I'm going to give port number 2000. So 2000 is the default port number what you will have to use to be able to set up the client side communicating with the server of CARLA. And if you use 2001, it might not work, because 2000 is by default, this port is dedicated for CARLA to be able to communicate with the clients, right? So this is the one that you need to use by default, unless you have somehow changed it or you want to change it. All right, so that's the first line, and that's gonna set up the client of our CARLA. But the issue here is when you set up the client, as I just mentioned, you are running the server and client on the same computer. So it can take up some time, a little bit of time to be able to set up. And if your Jupyter notebook see that it did not receive any response within first 1, 2, or 3 seconds, what it's going to do is going to show you an error, right? That it was unable to communicate with the CARLA server. But it takes a little bit of time. So what we are going to do is we are going to do another method under client, and we're going to do set timeout. Let's just say 15 seconds, right? So what this command is going to essentially do is it's going to tell your Jupyter notebook to wait for 15 seconds to be able to set up the communication with the CARLA server. And then we're going to write another line, because we need to operate on this server world, right? So this world, we're going to call this the world in CARLA. And we want to do operations in this world. We want to set up a vehicle. We want to deploy some non-player vehicles. We want to set up some pedestrians and so on. So what we're going to do is we're going to set up a variable called world, and we're going to again go back to our client, and we're going to type get world. So what the get world method is going to do is basically it's gonna load the prerequisites inside your world variable so that you can directly communicate with this instance to be able to run different operations on your world. So right now we have 3 lines. So these 3 lines should set up the client side, and it should store all the things that we need inside the world variable so that we can just communicate with the world variable and make changes to the world that we see here on the left side. So I'm going to hit Shift Enter again and run this cell. And as you can see, it took a little bit of time for this to go from start to cell number 2 because, as I mentioned, it takes a little bit of time to set up the client side. So you're not going to see any output here, but as long as you're not seeing any error, that means the client has been set up to communicate with the server. So now if we run any commands, it's going to do that operation on the world. Now, before going into the next couple of things, what I'm going to do is I'm going to change my browser window and go back to the CARLA documentation that I initially showed you. So you see that on the left side, we have this tab where you have introduction, quick start package installation. We already did the installation. You have the first steps, you have the building CARLA. So as I mentioned at the beginning of the workshop, if you want to have the developer mode of this CARLA software, you want to create your own devices, create your own roads, then you have to build it from scratch using the building CARLA. And you will get the installation information for the developer mode here under the building CARLA tab. So, but for now, I'm gonna go inside this first steps. I'm gonna click on it, and you open up this page where you have the 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 CARLA developers teaching you the first steps of using CARLA. So if I'm scrolling, so you see that the first section is launching CARLA and connecting the client, which we just did. So, so it's showing the command in Linux-based operating system, but in Windows, you don't need to run the shell script. You can just double click on the carla.exe as we did to open up this server, right? But for the client side, we need to write these lines, client, CARLA client, localhost port number 2000, and then to be able to get the world, we need client.getWorld method to be able to communicate with the world. So that's basically the first 2 steps that we have done. But here in the middle, we put another line, which is the client wait time. So, and we set it to 15 seconds to be able to set up the connection. All right, and then if I scroll down here, you see that it talks about loading a map. So right now, by default, we have a map here. But if you want to change the map to something different, there are 2 ways to do that. First of all, you can do it from your shell script, but we already have set up the client, so we don't need to do that. We can actually just load this command to change the world. So let's see how it works. So I'm going to copy this from here, client.load_world and town 5. So what it's going to do is going to load the town 5 from the CARLA blueprint, right? Blueprint library. So what is a blueprint library? It's basically the library of all the different type of car models, the town models, the weather models that you have inside CARLA. So we're going to copy this command from here, client load world, town of 5, and we're going to put this command here. And we're going to hit Shift Enter to run the cell. Now, once you run the cell, know that it will take a little bit of time to change the world because it's going to destroy this world in server and it's going to open up a new world in CARLA that is called Town 05, which is already set up inside the CARLA server. So you see that the timeout of 15,000 millisecond, 15 second has been passed, and that's why it's showing me an error. So what I'm going to do, but even if it does show you an error, you see that the environment here just changed. So keep your patience and wait a couple of seconds or maybe a minute or two to see if because it should be able to communicate with your server side and it should be able to change the map. So you see this is a different map. So I can go down. So I'm underground right now. I'm gonna go up. And then if I use my WASD key along with my mouse cursor, I'm gonna be able to navigate through this wall. So this is another world that as you can see. Let's try to open up another world here. Let's try town 06. So I'm gonna hit Shift Enter again. And okay, so there's no town on town 06. Uh, that's bad luck for us. Let's go back to the first steps and see what kind of maps we can actually load. So there is a blueprint here. So if you scroll down, you see the blueprint here. But I think, yeah, if you scroll further down, you see that there's a section on choose your map, and this lists all the different maps. So town 1, 2, 3, 4, 5, 6, and so on. So it says the 6 is available, but for some reason we are not getting town 06. Let's try a different town then. Let's try town 3. Let's try town 3. I'm gonna copy town 3 here, and I'm gonna put town 3 here, and then I'm gonna hit Shift Enter again. So this time I did not get the error. That means town 3 is in this Carla version, and it's gonna try to open up that town 3 on this world map here on the left side on the server. So okay, so you see that this time we were able to communicate with the client and we got response within 15 seconds. So we did not have any error here, but even if you have an error, that's not a problem as long as you were able to change the server side, right? So here you see that we are in another different world here. This is another urban world. So you can feel free to play around with it, change and try different ward setups here. And as I showed, so these are the default wards that are already being set up with your CARLA installation. But I think you might not see anything if you use Town 08 or Town 09 or Town 11. But the other ones should work fine, although we tried the Town 05 and it did not come up. So some of the towns, but you should be able to open up most of the towns here because that's what they're saying that are available with this version. But sometimes there are bugs that they have to fix from their side on the developer side. So some things, even though they say it in the documentation, may not be available when you are working on it, and that's fine. So I'm gonna go and change back my map to town 10 because I believe that's where we started from. Okay, town 10 did not found. I think it's town 10 HD OPT if I'm not wrong. Let's see. That's not the town 10 HD OPT. Let me try town 10 HD. Okay. All right, so we are back to our world. So the world we started with, it's called town 10 HD. So this is the world. So I'm back to this world again. So that's where I'm gonna run all my commands. All right, so now what we are going to do is we are going to try to set up a vehicle in this world, but not like we did before. So before we ran the generate traffic.py and it created some random number of vehicles on the road that were running on autopilot, but we need to be able to control those vehicles, right, for our simulation. So what we are going to do is we're going to create our own vehicle here, not the random ones, but the one that we would like to set up here. So for that, we first need a location where we are gonna deploy the vehicle, where we are gonna put the vehicle, right? So to do that, let me see if I can go back to the CARLA documentation and open up the window where you do this. Okay, spectator. Okay, they do not have that part here. They have add sensors, but they do not have the vehicle adding here. Okay, I see that the spawn points are there. Okay, yeah, so you can copy from here. All right, so you see this section on the left, on the right side of my window, basically the first steps with CARLA. if you go down and if you click adding NPCs, it takes you to the section adding NPC. NPC stands for non-player characters. It's just a term used in CARLA for different things like vehicles, sensors, and so on. So what we are going to do is first we are going to spawn a vehicle. By spawning, meaning what I mean is that we are going to deploy a vehicle on this road that we see. Uh, but we need two things for that. First of all, we need to know where we are going to put the vehicle. So we need the location on this map that we see. And we need to know what type of vehicle or which make, model, or year of vehicle we are going to deploy, right? So to do that, what we're going to do is we're going to import the CARLA blueprint library, because the blueprint library is where all these different vehicles, different worlds, different type of sensors are included. And you can take any of those sensors or any of those vehicles and put it in your CARLA server on the world. So we're going to copy this code here. So get the blueprint library and filter for the vehicle blueprints. So I'm going to copy this whole thing. Control C. And then I'm going to go back to my CARLA workshop and put it here. So vehicle blueprints. Vehicle blueprints is a long name, so I'm going to just name it vehicle BP. So var.getBlueprint.library. So that's our blueprint. So let me go step by step. So what get blueprint library does is this method talks to the world variable, and then it gets the blueprint library that is available inside the world. And then if you put a filter method, you can basically search through or filter through all the available libraries there. So I'm going to filter for vehicle. So that's why we have this inside the code, we have this uh, uh, star vehicle star. So what it's going to do is it's going to filter through all these different components available in the blueprint library, and it's going to load them up, load all the things that starts with vehicle. So all these different types of vehicles will be loaded in this vehicle blueprint. And then if you want to use one of the blueprints from there, we can use that. So let's see. I'm gonna type another line. I'm gonna type vehicle blueprint. Let's say vehicle blueprint, and let's see if you can print the different blueprints for the vehicles. And then I'm gonna hit Shift Enter. So as you can see that it has printed all these blueprints. So actor blueprint. So by default, CARLA calls. So in CARLA, we call the vehicles, pedestrians, sensors, all these things, we call them actor. And blueprint is essentially the model of a particular actor. So you see that the ID for the first entry here is vehicle.audi.a2. So that's the Audi A2 vehicle. So if we want to use that, we can use that here. There are other different types of vehicle as well. Nissan Micra, you see here another vehicle, Audi TT, and then there's Mercedes Coupe 2020. There is another Mercedes Coupe here. There's BMW Grand Tourer, and all these different type of vehicles that you can use. So all those vehicles are listed here. If you want to look them up directly from the CARLA documentation, what you can do is you can go inside this. So on the left tab, you have this CARLA topics. So you have actors, right? So if I click on actors, so it's going to open up this page, what it says, actors and blueprints, and it has all these blueprints from different things. So let me scroll down and see what they have. Okay, type of actors, sensors, traffic lights, vehicles. Okay, so CARLA.vehicle. Okay, so it opened up the vehicle method, and inside the vehicle method, we have these different throttle steer. We are going to use some of them in our tutorial today. So I'm going back. Going back again. Okay, I just saw it. There was a blueprint library. Did it go? Okay, all right. Here. So under resources, you have this tab called blueprint library. So if you click on this blueprint library under resources, essentially you're going to open the blueprint library. So inside the blueprint library, you actually have all this information. So you see that we start with controller. So there's this controller by default in CARLA. You have a sensor in the blueprint library. So you have different types of sensor. You see that this one is a depth sensor. There's a DPS camera. There's instance segmentation camera, normal camera. There's RGB camera, optical flow camera. There are LiDAR that you can use, raycast LiDAR. There are semantic LiDARs. There are collision sensors, GNSS sensors, IMU sensors that you can use. I'm going to keep going down here. There's some static things that you can use as well. I'm not sure what it does. Going down, so you have this vehicle. All right. So here, in the blueprint library, you have this vehicle. So you see that all these different type of vehicles are available. So you have Audi 2, you have Audi e-tron, you have Cross Bike, Grand Tourer, Carla, you have a Carla Cola, funnily enough, a Carla vehicle here. Uh, you have fire truck. So you can actually put a fire truck there. You have Impala and so on. So many different things, right? So I'm gonna go back to this our Carla workshop file today. And then what I'm gonna do is I'm gonna find a fire truck. So we're gonna type fire truck. So and then instead of filter method, I can actually use the find method. So it directly finds the fire truck for me. So and then I'm gonna hit print vehicle blueprint just to be able to see if it was successful enough to find the fire truck. So it did not find the fire truck. Let us try vehicle.firetruck. Okay, it was not able to find the fire truck. So I'm going to go back to the blueprint library. So it has vehicle Carla Motors fire truck. I'm going to copy this whole thing. And then I'm going to put it there. And let's see if it finds it this time. All right, it was able to find the fire truck now. So you might have to find out the right name for it to be able to find it in the blueprint library. If you type a wrong name, it might show you an error. So right now we got the blueprint library for the fire truck. So now we can spawn the fire truck on our world here. So what we're going to do is we're going to get some spawn points. So we're going to type a variable spawn points, and then we are going to call in the world, and we're going to do get the spawn points. So first we need to get the map. So we are going to use the method called get map. It's going to get the map, and then inside the map you have all this road infrastructure and everything, and you need some spawn points, right? So what it basically means is that where can you place your actors, like your vehicles or pedestrians? So you cannot place your vehicle in the sky, maybe, or you cannot place your vehicle on top of the building. You need to be able to place it on the road, right? So it's gonna get you the available spawn points in CARLA where you can actually deploy your vehicle or actors. So I'm gonna type in this get spawn points method. So the spawn points variable is var.get map get spawn points. So what this is gonna do is it's gonna collect some points where you can actually deploy your vehicles or pedestrians or so on. And then let's just check, like print the spawn points to be able to see what we got inside the spawn points. All right, so right now it's printing two things at a time. So I'm gonna comment out the vehicle blueprint part and just keep the spawn points. Let's print it again. So you see it actually gave us all these different spawn points that we can use. Let's see how many of them are there. So I'm gonna use the length to see the size of this list. So once we use the get spawn points, we have these 155 different spawn points. Basically, these are points where you can deploy the vehicles on the map. All right, so now we have all these spawn points loaded. What we are gonna do is we're gonna deploy the vehicle. So we're gonna type, oh, I'm sorry. going back. So we're gonna deploy the vehicle. For some reason, it changed my. Okay, I'm gonna type in a command, deploy a vehicle, and then I'm gonna type in my vehicle variable, and then I'm gonna call in the world, and I'm gonna try to spawn my vehicle here. So I'm gonna try spawn method, try spawn actor, try spawn actor. And then it takes two arguments. So the first argument is what type of actor you want to put there. What is the blueprint of the actor, right? So right now our blueprint is the vehicle blueprint. So I'm gonna type in vehicle blueprint. And then the second argument is essentially where do you want to spawn it? Where do you want to put the vehicle? So as we saw, so under spawn points right now we have 155 different points where we can spawn the vehicle. We just need one of them. So what I'm gonna do is I'm gonna put a random location. I'm gonna choose a random location, uh, random.choice, and then I'm gonna pick one of the points from the spawn points randomly, right? But to be able to run this, we need to import random. So in the first cell, I'm gonna type in import random now and hit Shift Enter so that we have the random function available to us. And here we have the vehicle. So we are using the try spawn actor with the vehicle blueprint of a fire truck. And we are going to randomly pick one of the 155 different points available here. And we're going to put our vehicle there. So let's hit Shift Enter. Okay, so spawn points. Okay, I think I made a typo. It should be SPAWN spawn points. Okay. All right. So as you see, the sale ran successfully. So what it tells me is that the fire truck is already in this world, but let's find out where it is, right? So I'm gonna go up on my server, and I'm gonna just navigate through the world to see where the fire truck is. It should be somewhere in the world. Okay, okay, there it is. I see here. Now, because I randomly chose a location for the fire truck, so if you use the same method, your vehicle may or may not be here. It should be in one of the 155 locations we just chose. Uh, so here we have our fire truck, CARLA Fire Department. So this is our fire truck. And okay, let's go up. So this is our fire truck, right? So we have spawned a vehicle here successfully. Let me know if you have any questions because I'm just showing the different steps. I'm not sure if you are able to follow. So can someone unmute and let me know if you are able to deploy a vehicle? Anyone? John, Araf, Mamoon, I see Mamoon. Or anybody else? Were you able to deploy a vehicle? I don't see any response. Uh, Anybody was successful to deploy a vehicle on the map? Okay. Yeah, feel free to take your time and let me know if you ran into any error. Feel free to interrupt me, and I'll try to resolve the issue with you. Because the best outcome of the workshop will be if you can run these commands with me. I know it's a little bit difficult to at the same time look it in the Zoom window and then at the same time code and navigate your laptop. But try your best. I would recommend trying your best if you can follow the codes with me. At the end of the workshop, I'll of course share all these scripts that I'm writing with you. So you can directly use them on your computer to be able to see if you can do these things that we are trying here. All right. So what we are going to do now is we're going to see if we can run this vehicle, right? So the easiest way to operate the vehicle is to set it up on autopilot. So we're going to do vehicle dot set autopilot method, and we're going to put the argument true. So if you put false here, then it will not set up on autopilot. If you put true and then hit shift enter, what it's gonna do is it's gonna run the vehicle. So it might take a little bit of time to be able to communicate, but you see that the vehicle has started running. And if we want, we can follow the vehicle. It's very much like a game. All right. And you see that there's a yellow light right now. So the vehicle has stopped here in the signal. So it's waiting for it to turn green, and then once it turns green, it's gonna start again. All right. So for now, I'm gonna set. I think we can keep this vehicle set autopilot at true. So let the vehicle work on this world. Okay. So once the vehicle is running, if you want to check the position of the vehicle, so you can do that. So let's say check the current position of the vehicle, right? So what we're going to do is we're going to type in this variable called vehicle position, and we're going to do vehicle method get transform. So what get transform does is basically gets the location for you. Should be vehicle position, all right? And then I'm going to type print vehicle position and then hit shift enter. So what this is going to do is basically give us the location of the vehicle. So right now the vehicle is in this location. So it is giving us the X, Y, and Z coordinates of the vehicle. And it also has a component that is rotation. So basically the pitch, yaw, and roll. So at what location? Because you know it's a simulated world. It works with a physics engine at the background, which is Unreal Engine. So it has all this physics involved in it, where you can have the pitch, yaw, and roll, right? So your pitch would be like this, and then yaw will be like this, and roll will be like this. So at what condition the vehicle is. So it is telling you exactly at that instant where the vehicle is, at what rotation or orientation the vehicle is. So you can run it anytime. So if I run this cell again, you are going to see that the location and the rotation are changing. So you see that the location has changed, the rotation has changed too, because the vehicle is on some different other point right now. So that's how you look up the position of the vehicle, and that's going to come handy when we are trying to set up like different sensors and so on. All right, so right now our vehicle is running in this world and we don't know where it is, right? So there it is. We see it is there hiding behind this building, I think. Oh no, it's not here. Okay, let's see where it is. Let's go up in the air. Okay, there it is. Okay, so the vehicle, the fire truck is operating here, but we don't want to do this manual control of the spectator view because that's very tiring to do. If you want to follow a vehicle closely while it is operating, then I'm gonna put a piece of code here that I've already written. So what this piece of code does is basically it sets up the spectator view of the vehicle to observe the vehicle movement. So it will move along with the vehicle. So you will see that this window you will not need to manually control. It will directly follow the vehicle as the vehicle moves. So we have written this follow vehicle function, where first we are getting the spectator set transform method, and inside that we are getting the CARLA transform. We are getting the current location of the vehicle using the vehicle get transform dot location, and then we're gonna add some offset to that. We're gonna put it behind the vehicle to make it look very much like you are playing a game, like a Need for Speed or something, where you are basically following the vehicle from behind, right? So it's going to set up a window like that where you can directly have your spectator set up behind your vehicle, following it closely. So you're chasing the vehicle as it operating on the world. So I'm gonna put this code here, and then I'm gonna hit Shift Enter. And what it does, as you can see, we magically appeared just behind the truck, but we are so close to the truck, it's very difficult to see anything. So feel free to play with these variables, like these numbers here, -6, the location. So if you change the Z, it's gonna take you. If you increase Z, it's gonna take you up. So if you're up the vehicle, above the vehicle, then you'll be able to see what the vehicle is seeing in front of it. So feel free to play with these numbers here uh, to set up your spectator view. So this view is what we call the spectator view. All right. Okay, and then what we're gonna do is we don't actually want. Okay, let us try something here. Let me see. Mm. Okay, let us try to do something. We're gonna set up a route planning, like what Dr. Chaudhary mentioned about. So route planning is basically going from point A to point B. So selecting the most efficient route, or that route that will take the least amount of time, what we typically do with Google Map or Waze. So that's what we're gonna do. We're gonna set up a route for this particular vehicle. And let me see. We're gonna set it up to to go from the spawn point, say, to this location that we recorded. So the vehicle went to this location at some point of this simulation. So we are gonna set up a route from this random spawn point to this vehicle, to this location. So before doing that, what we are going to do is we're going to destroy this vehicle. And you can destroy the vehicle anytime by using the vehicle.destroy command. So if I, okay, there was a typo, vehicle.destroy, right? So what you see is that it destroyed the vehicle, but it's showing us an error because what's happening is that this function is running continuously and it's trying to track the vehicle location. So as soon as you don't have a vehicle, this function will not know what to follow, right? So then that's why it's showing me an error that the vehicle dot get transform returned a non-type object, right? Because the vehicle does not exist anymore. We destroyed it. Okay, but that's not a problem. So we just destroyed the vehicle. So now right now we don't have anything on the road here. But that's fine. We're gonna set it up again. So before we go to the route planning part, what I'm gonna do here is I'm gonna change this cell to a markdown. I'm gonna write route planning. So this is going to be a section for our workshop today. Let's just say route planning. Okay, so in this section, we'll do the route planning. So to do the route planning, you actually need to communicate with your, you need to go to a particular folder where the route planning function is. But we changed the folder because we are already inside the folder that we created in our desktop, right? So if we need to find a different file or anything that is in a different directory, we need to do it through the command prompt. So what we're gonna do is we're gonna import sys. So what it's gonna let us do is it's gonna let us append any path that we want to, so that we can directly work with that path or anything that is within that path. So we are gonna do path.append, sys.path.append, and then we're gonna type is the location to the Python API. So I'm gonna go inside my CARLA root directory here. It's inside my C drive, inside the CARLA folder, and there's this folder called Python API that looked into previously, and then inside it we have the CARLA folder. So I'm gonna copy this location from the address bar, and I'm gonna go back to the code here that I'm writing on Jupyter, and I'm gonna put this address here. So what this is going to do is this is going to put this location on your system or your path variable or environment variable. And then from there, we can actually import what we need to import for route planning. So there's a particular package that we need to import, and it's inside the agents.navigation dot global route planner, and then from that location we need to import the global route planner. All right, so this particular Python script is going to be enable us so that we can actually set up a route and then we can trace the route. So before, our vehicle was just running autonomously in random paths, but this time we want to set up a particular path for it so that it goes from a point A to point B that we can select. So I'm going to hit Shift Enter here. Okay, we got an error. Let's see what the error is. Okay, so the error I'm getting is because of this spectator view, because it's trying to find a vehicle and it was not able to find the vehicle. So to be able to resolve this issue, I'm gonna restart my kernel. So I'm going to this kernel option here at the top, and I'm gonna restart the kernel and clear outputs of all cells. Let's do that. Restart the kernel. All right. So we just restarted the kernel. Now let's run the first two cells anyway, because we need to import CARLA, we need to import random, and we need to set up the client side to be able to communicate with the server. Okay, so after we have these, yeah, let us run this cell as well, because that's where we are setting up the vehicle, right? So instead of putting it on the random position, what I'm gonna do is I'm gonna put it at one location so that I don't have to go through the map every time and find out where it is. So I'm going to use the first spawn point here from the list, and I'm going to run this cell. So you see the vehicle just arrived here. So the beauty of this is every time I want to spawn a vehicle, and if I use the first point from this spawn points list, it will always come to this particular location, right? So I don't have to look through the entire wall to see where it dropped. So it will drop at the exact same location every time. Okay. And we're not going to set up the vehicle set autopilot yet because we want to set up a path for the vehicle to follow. So instead, what we're gonna do is we're gonna, oh, we just actually, the position is removed here. So let me do one thing. Let me run the vehicle.set autopilot. And then I want to record, I'm doing this because I want to record the position of the vehicle. Okay, so it's driving here. It's going through this path. Let's see. Okay. And then here, I'm just gonna print the position of the vehicle. Just print the position of the vehicle. So this is the current position of the vehicle. So what I'm gonna do is I'm gonna copy this whole thing here. Let me copy this whole thing here. Okay, sorry. The location and the rotation. And then I'm gonna put it on a notepad so that later I can use it. Okay, keeping it there. And then I don't need the vehicle actually right now, so I'm gonna destroy the vehicle. Okay. And then because I destroyed the vehicle, I basically ran it for a couple of seconds to have a point on the world where we can set up the route. But I'm gonna rerun this cell to get the vehicle back at its original location. And then I'm gonna go here in route planning. And then in route planning, we need to trace a route, right? So a route is made up of 2 points, a starting point and a destination point. So we need to give it at least 2 points. Let's say the point A. Let's say point A, point A. So point A, let us say the point A is the first spawn point. So the spawn points, that's where the vehicle is right now. And then let's say point B is basically what we So it should be CARLA. So what we copied here. So let us just copy the X, Y, and Z. We don't care much about the rotation. Oh, so I'm gonna type Carla dot location, and then I'm gonna put the X, Y, and Z values there. So right now what it's gonna do is it's gonna set up the first starting point where the spawn point is right now. So where the vehicle, we can see the fire truck. So exactly that's our point A. Oh, so that's our point. Yeah, so that's the spawn point, point A. And then we printed this location before when the vehicle was around this corner over here. And then we want to set up a route that will let the vehicle go from where it is right now to that particular point. So we have our point B set up there. And this just run the cell. So we have our point A and point B. Now we have to set up the route. So let's create a section here, set up the route, and then we need some sampling resolution. So to be able to, because when you have a route, what you typically do, or what the software typically does in autonomous operation, it picks up a couple of waypoints along the route that it's gonna follow through. So you have your starting point, you have your destination point, but connecting these 2 points needs to be a line that the vehicle is going to follow, right? And how to create a line? It's not a straight line, so it can be a curved line. It can go through many different roads to be able to reach point B. So what you need from point A and point B is a set of waypoints that are navigable by the vehicles, right? So the points need to be on the road. The points cannot be on top of a building, right? Or it cannot be under the ground. That point cannot be navigated by a vehicle. So what you need between point A and point B is a set of points that you can actually follow through the road. So and those points are called waypoints, and you need a resolution at what resolution these points are going to set up. So I'm going to set up sampling resolution 2, but feel free to play with different other options. And I'm going to call in the global route planner, global route planner. And the global route planner takes in 2 different arguments. First of all, uh, the map of the world, right? So where in which world you are right now. So you need the town map basically. So how do you get the town map? So the town map is basically, we did it before here. So the world.get map. So this gives you the map of the world, right? So I'm gonna copy it from here, world.get map, and then before I complete this line, I'm gonna set up a variable called town map, and I'm gonna put the world get map there. So now the first argument of our global route planner, we can put the town map there. So it essentially tells which map we are working on. And then the second thing you need to have is basically the sampling resolution. So we already set up this. Okay, made a typo, sampling resolution. So I'm going to copy this sampling resolution variable and I'm going to put it as an argument to the global route planner. So what it's going to do is it's gonna discretize this town map based on this sampling resolution. So then we can trace or create a particular path if we want to. Okay, and then what we're going to do is we're going to set up the route. So the route is essentially going to be this instance, and then we are going to create the route by tracing points, right? Uh, I'm sorry, it's going to be not points. So it's going to be trace route. And then here you need to give 2 arguments. The first argument is basically the starting point, and the second argument is the end point. So the first point we want is point A, and then the second point we want is point B. So it's going to go from point A to point B, and it's going to set up the route there. And then we just don't want to create the route at the back end, but we also want to visualize it, right? That this is the route that we are tracing. So what I'm going to do is I'm going to put this boilerplate code here that gives you the opportunity to be able to see the waypoints. So we already created this route variable. So what this does, it runs a for loop for each waypoint in the route. So this route is basically a set of waypoints that the vehicle is trying to follow. And we're going to pick one of the waypoints each time as we are executing the loop. And then we're going to do this while.debug.drawString method. And we're going to pick the waypoint that we are working on, and we're going to transform that location into the coordinates. And then we're going to put this mark there. And then the rest of it is just how you want this symbol to appear, in what color, for how long, and whether you need a line connecting them or not. So all those different options are already set up. So what we're going to see is that we are going to see some symbols like this from point A to point B on the road. That's going to tell us, okay, that this is the route that the vehicle is going to traverse, right? So we're going to run this cell of code, and we see that the global route planner is not found, and that the reason is we did not import it, right? So we have to run this cell first, import sys.pathappen. So let's run this cell first, and then I'm just going to read on this cell anyway, and then set up the route. We're going to run this cell again. Okay, so it's saying that it probably does not know what point A or point B is. So get waypoint plus CARLA location. Oh, I think what it tells us is that, okay, let us try something here. I have a feeling that the spawn points are not coming as it should. So I'm going to print what we are going to get when we do these spawn points. Oh, there's actually an easier way to do this. Let me run the vehicle position one more time, because that's where the vehicle is right now. So I'm going to run this block of cell here to get the current location of the vehicle. So this is the current location of the vehicle. So I'm going to copy this entire thing, and I'm going to put it as point A. So CARLA dot, this is the location. And then I'm going to run, we don't need this cell anymore. So I'm going to delete this particular cell. All right. So here, CARLA dot location, I'm going to run this piece of cell. It sets up point A and point B, and then I'm going to run this piece of cell again. All right. So as you can see that on the road right now, we have these dots that basically are telling us where the route is, where the starting point is, where, oh, I'm sorry. Oh. Okay, let me see. Okay, there it is. Okay, so you see that it goes from the current location of the fire truck to the location that we want to go, right? And it has set up a set of waypoints that the vehicle is going to follow. So right now, if we simply run vehicle dot set autopilot, and turn it to true, then what it's going to do is it's gonna operate the vehicle going from point A to point B. So I'm going to run this piece of code. As you can see, the vehicle has started moving, and it is essentially following the route from point A to point B. Yeah, but what's going to happen is it's not going to stop there, because you have set up a vehicle set autopilot to true. So it's going to keep running till you destroy it. So we're going to do vehicle. Oh, we don't need to destroy it right now. Okay, let's destroy it, because we're going to try some new things now. So let's destroy the vehicle for now. All right, so the vehicle is gone. All right, so now the next thing we're going to do is we're going to see how we can set up some sensors, right? But before we move on to that, please let me know if you have any questions. Okay. No, I'm going to change it to a markdown. So just creating a new section in my notebook, and I named it CARLA sensors. So we are going to try out different type of sensors in this block. So the first thing we're going to work on is definitely the most popular sensor for autonomous vehicle, which is camera. So we're gonna create a subsection here that's called camera, and let's try out the camera option. So we need to import some libraries for this. And let's say that we are starting this part of the code uh, from nothing. So I'm going to restart the kernel. So this piece of cell, this couple of cells that we're going to run on this block, or we're going to write here, they don't know anything what happened before, right? Because we just restarted the kernel. And we are going to import then CARLA. And then we're going to import math, because we're going to do some math operation. We're going to import random. We're going to import the time package to be able to track the time. And then we will use the numpy a lot. So we're going to import numpy as np. And then because we are working with camera and we want to see what the camera is seeing, we also need the OpenCV. So we're going to import CV2. So these are the packages that we need to import for this part of our workshop today, where we're going to basically set up a camera. So let's run this cell. So we have imported all the files. Now, just as before, we need to set up the client first, right? So I'm going to go back on top here where we wrote this piece of code to set up a CARLA client. And then I'm going to paste it here and hit Shift Enter. So basically, we set up the client side again, communicating with the server now, right? And then because we're gonna use the blueprint quite a lot to get the vehicles, to get the sensors, to get the pedestrians if we need to. So we're gonna assign a variable to the blueprint library. So the blueprint library is within the world. So we're gonna do world and then get the blueprint library, right? So basically what this variable will have is it will have everything that you have in the CARLA blueprint library. And then you can pick anything that you want to from there. You can pick vehicles, you can pick sensors if you want to. And again, we're gonna set up the spawn points, right? So we're gonna set up the spawn points. We're gonna do the var.get map method. And under the get map method, we're gonna do get spawn points, get spawn points. All right. So inside the map, we are getting the spawn points now, and we are saving them in this variable called spawn points, so that later we can pick points from there. And then we're going to run this piece of cell. So we have the blueprint library, we have the spawn points. Now let's pick a vehicle. So I'm going to pick a vehicle just like before, and we're going to pick it from the blueprint library. So we're going to do the blueprint library, and we want a specific vehicle in mind this time because we already know which vehicles are available. So the vehicle I'm going to use is vehicle, but you can use any vehicle, of course, that you would like. But I'm going to use Lincoln MKZ 2022. 2020. So vehicle is a Lincoln vehicle, MKZ model of 2020 year. So we got the vehicle blueprint. So let's call it a vehicle blueprint. And then we're going to set up the vehicle, right? And as I mentioned before, to set up a vehicle, you basically need to do the world try spawn world dot try spawn points. Sorry, try spawn actor. I'm sorry, try spawn actor. And then basically you need to give it two arguments. First of all, where to spawn and what blueprint to spawn, right? So the first argument is basically the blueprint. So we're going to give it the vehicle blueprint. And the second argument is the spawn points, right? And this time we're not going to choose a random point. We're going to pick the first point because we need to know where the vehicle is. So hopefully the vehicle is going to arrive right here where we're looking at. That should be our spawn points, 0. Oh, I typed spawn points. Okay. So let's see if we get a Lincoln vehicle here. So as soon as I run the cell, if you saw that the vehicle just dropped. So now we have this Lincoln MKZ of 2020 on our world. And now we can set up a camera here. So for camera, we need to do the same thing as we did with the vehicle. So we need a blueprint. And there are many different types of cameras available as we we saw on the blueprint library, right? So if you go through this documentation and go to the sensor section, sensors, this is sensors. Okay, so you see that all these are different type of camera. There's a depth camera, there's a DVS camera, there's an instance segmentation camera. Basically, it's going to tell you what instances you have directly. So the good thing about CARLA is because we are simulating the world here, we already know the ground truth. So if you want to run some neural networks, if you want to train some machine learning applications, you always need some ground truth to train it, right? And in simulation, because you are simulating the world here in CARLA yourself, you know the ground truth for sure. And then if you want to train your machine learning models on that, you can just directly get those data from the simulator, and then you can train your AI models. So what we're going to do is we're going to use the regular RGB 3-channel camera. There are actually 4 channels. We're going to talk about that in a minute. But this is called the sensor.camera.rgb, and that's what we are going to use for now. So let's try to find out the blueprint of RGB camera from the blueprint library. So we're gonna look for this particular camera, which is the sensor camera RGB. So I'm just gonna copy this text from here, sensor.camera.rgb, and then I'm gonna put it here, sensor.camera.rgb. So we're gonna get the blueprint of the camera, RGB camera. All right, so just like before we deploy the camera, we need 2 things. First of all, what type of camera we are going to use. So that's the blueprint. Blueprint gives us that. And the second thing is where do you want to put the camera, right? So we need a camera location then. So I'm going to call it camera transform, camera trans. And then what we need is we need to set up the camera on the vehicle, right? We need to attach it to the vehicle. So if I give a particular location here on the map, what's going to happen is that once we start driving the vehicle is going to drive by, but the camera will stay at one location. So that's going to be ridiculous. So what we need to do is we need to attach the camera to the vehicle. And that's why we need to give the location of the camera with respect to the location of the vehicle, right? And for that, we are going to first set up uh, this variable here. We're going to give the location, and then later we're going to give it attached to the vehicle so that it knows that it has to attach to the vehicle. So for now, we are going to just give it a location. And we want say, for example, we want the location to be 0.4, and then Z is 1.6. But feel free to change this location. So what's this going to do is, with respect to the vehicle, it's going to change the location of the camera. So if you increase X, it's going to go down the path along the vehicle. If you decrease X, it's going to straight go up along the route of the vehicle. If you increase Z positively, that means the camera is going to go up in the air. If you decrease Z, it means that it's going to go down the location in terms of altitude, right? So feel free to change the X, Z, and any Y coordinates too. So Y coordinate is going to just shift the camera left and right. So for now, we are gonna set it up a little bit ahead of the vehicle. So we want it to be the front camera. So we set X to be 0.4. If we need, we can increase the distance. And then we don't need we don't want the camera to be on the ground, right? So we set up an altitude for the camera. So it should be 1.6 meter from the vehicle's center of gravity. But now, right now, if I use this transform, what it's gonna do is gonna set up the camera at the exact location of CARLA for this given coordinate, right? And the camera will stay there forever. It will not move along with the vehicle. To be able to ensure that it moves along with the vehicle, what we're gonna do is we're gonna again, so right now we are setting up the camera. So just like the vehicle, when we did the world try spawn actor, we're gonna do try, or this time actually we can do a spawn actor because we know exactly where to attach the camera. So the reason we used try spawn actor before is that if you already have another vehicle at a particular location, And then if you try to spawn another actor at the same location, it's going to give you an error, right? It's going to have a collision because something is already occupying that location on the map. So that's why we used the try spawn actor before, so that if it fails to spawn there, it will give you an error that we could not spawn the actor there because something already exists there. But this time, because we are going to set it up at a location that has a particular offset from the vehicle center of gravity, we don't need the try method anymore. We can directly spawn the actor, but you can use try spawn actor as well. There's no issue with that. So we're gonna give the first argument just like before for the vehicle. We're gonna give it the vehicle, the camera blueprint, and the second thing we need to give is the camera location, right? So the camera location is this camera trans variable. So I'm just gonna copy this here, and then we need to set the attach to method to vehicle, attach to argument to vehicle. So what this will tell Carla is that you need to set up this camera, but you need to attach it to the vehicle. Sorry, there's a typo. You need to attach it to the vehicle, and the vehicle is this vehicle that we set up, right? And then you are giving this transform of the Carla location just as an offset. So it will know that okay, I have to attach to the vehicle, and I have to offset it from the center of gravity of the vehicle by this amount. So I have to add x equals 0.4 to the x coordinate of the vehicle center of gravity, and I have to add this z coordinate to the z coordinate of the vehicle to set up the camera. So that's what it's going to do, this attach to vehicle method. And then I'm going to run this piece of code. Okay, there's an error. So it's saying that there's no world uh, uh, object because probably somewhere I type world with capital W. Let me see. Oh, I actually misspelled spawn. That's why it's giving me the error. So I'm gonna do spawn actor. All right. So the camera has been spawned, but can we see the camera? No, we cannot, right? So if we move closer to the vehicle, let us see if we can see the camera. Okay, we don't see the camera. Okay, yeah. Yeah, we don't see the camera because it's just a sensor, so it's too small for us to locate from this world. But what we can do is we can definitely look at the view of the camera, and that's what we're going to do here. So we're going to look at what the camera looks at, right? But to be able to do that, um, let us first do one thing. Let's first see if we can, even though we cannot, because we need to write a couple of lines of codes to be able to see the camera view. But before we move on there, uh, because we already deployed the camera, let us see if we can save the camera images. So that's what we essentially do in autonomous vehicle. Uh, so if you want to train, say, for example, a machine learning model for an autonomous vehicle object detection, like it will detect whenever there is a pedestrian or another car or a traffic sign. So you need images, right? You need annotated images. So you need images of the vehicle driving by or across the road and what the vehicle is actually looking at, right? So we need to see what the vehicle will look at. So first of all, we're going to set the vehicle to autopilot for that. So we're going to do the same vehicle set autopilot method, and we're going to give the argument true so that it runs autonomously. Oh, vehicle. So as soon as this cell was successful, you see the vehicle has started moving. So right now the vehicle is moving and the camera is looking from the vehicle front dashboard, right? But we don't see what the vehicle is seeing. So what we're gonna do is we're gonna save in a folder what the vehicle is looking at. So record the camera, record the camera. So, and then we're gonna do this camera.listen method, camera.listen method. And then we're gonna use this lambda function. It's actually coming directly from the CARLA documentation. So, but I'm gonna explain how we are doing this. So we're gonna use the lambda function with respect to image, and for each image that we get from the camera, by listening to it, we're gonna save it to our disk. So we're gonna use the image.save to disk method, and then we need to give where the location should be, right? So where do we want to save this? So right now we are in this directory, uh, the folder that we created, CARLA trials, right? So let's just say we want it to save here, but not just in the root directory. We want a new folder inside it. So let's just name it front camera, and then we want to save the images. So you just need to give it the name that will change from time to time, right? So we're gonna do image, and we're gonna save each frame of the image, right? So what this is gonna do is this is gonna create a front camera folder, a folder called front camera in our current directory. And then it's going to save up all the images. And where the images are going to come from? The images are going to come from the camera.listen method. So you are basically listening to the camera, and the camera will give you what? The camera will give you images, right? And the images will contain multiple frames. So you want to save each frame as a separate image in your folder. And that's why we're doing image.save to disk. And we're trying to save each frame by image.frame, and we are giving it a name that will change for each frame. Right, so right now, if I run this command, so it's not showing me any output because there's no output setup. But if I go back to this directory, CARLA trials, so for some reason it's not working in the CARLA trials. Let me see where we are right now. Mhm. I'm trying to check the current location. So it seems like mm, mm, mhm. I'm not sure where they opened this. Let us give the exact location. So this is the exact location, CARLA trial. So I'm going to put it in front of this address. I'm going to change this to, I think actually the backward slash should work just fine. But just to be on the safe side, I'm changing it to the double forward slash. Okay. So right now, if I run this command one more time, I'm sorry, Shift Enter. Okay. So if we try to listen to the camera, because we are already listening to the camera and we just set up another listen method, so it's giving us an error. So what we're going to do is we're going to restart our kernel here. We're going to restart the kernel. And then we're going to run this couple of cells one more time. So we're importing, we're setting up a client. Okay, so the client is set up. We're getting the blueprint and the spawn points. We're setting up the vehicle. So the vehicle is there. And then we're setting up the vehicle on autopilot. So the vehicle started moving, and then we're going to listen to the camera and save the images. So you see that my Anaconda is showing that it's trying to save the images. So let's see. Oh, it did not come up here because there is an error. For some reason, we're getting an error here. So let's see. So it's saying that value error unsupported format character P. Interesting. Hmm. Where is this P? I need to find out. So image save to disk C. Oh, CARLA trials. Okay, so this is a wrong directory name. So it's inside CARLA trials. And then inside CARLA trials, we want front camera. So let us try one more time. The location was wrong. So we're gonna restart the kernel. And then we're gonna run this cells one more time once the kernel is ready. So I see that the kernel is still not ready. So let us try to restart the kernel one more time. Mhm. Yep. I think the computer got stuck here. So let us do one thing. So let us just shut down all the kernels. Shut down all kernels. And then I'm going to close up my Jupyter notebook. I'm going to go back to the Anaconda prompt. Here is not here, CLS. Okay, and then I'm going to reopen my Jupyter notebook. Let's see. Jupyter notebook. Okay, and then I'm going to reopen the CARLA workshop file. So we see that the kernel is ready now. So let's try to run this couple of cells one more time. So import is done. We set up the client server. Let's create the blueprints. Let's get the vehicle. Let's get the camera. Let's set the vehicle on autopilot. And as soon as the vehicle is set on autopilot, we're going to run this camera.listen. All right, so it's saying that it is still getting that error camera.listen lambda, but let us check here. Yeah, the folder has not been created. Okay, let me try something. Let me try directly. There could be a typo. So I'm going to restart, shut down the kernel and restart the kernel. Okay, the kernel is ready. Set on autopilot. Front camera images. Okay, all right. So I think for some reason I made a typo before. So right now it has been fixed. So camera.listen, we are using the lambda function. We're calling in the image and we are saving the image to the disk. So if I go to my directory here in CARLA trials, you see that there's a new folder, front camera images, that we just created using the code. And if we go inside the front camera images, you see the recording has started and it grows very fast. You see that it's already, we have 225, now 230 images we have captured. So it's gonna go like that. It's gonna go very fast. So what we're gonna do is we're gonna destroy the camera for now. We don't uh, need it anymore. So we're gonna destroy the camera. Okay. So right now the camera has been destroyed and you see that we have collected so far 318 images of the vehicle. And if we open up the images, let's look at the images. So this is the image that we got. So we got the front camera view, and as the vehicle moves along the road, we are dynamically capturing the images, as you can see. So I'm just hitting next and going to the next image, so you can see that the images are captured as the vehicle moves along the route. Oh, interestingly, we have our previous Lincoln MKZ waiting here. All right, so that's because we did not use the vehicle.destroy. So if we don't destroy the vehicle, it's going to remain in the world forever, unless we close down the server, of course. All right, so we just saw how we can set up a camera, how we can get the images, save the images from the camera to our local directory or a directory where we wish to save them. Now, let's do another thing. Let's say that we want to look at the camera images. Actually, it's 12 o'clock. I have to finish within half an hour. So I'm gonna for the next couple of codes, I'm gonna copy directly and paste it there, and I'm gonna explain it so that it's going to be easier for me instead of typing line by line. Um, just hang around with me here. So what we're gonna do is we're gonna set up a camera callback function. So this is basically a camera callback function, and we're going to do the same thing for LiDAR and radar too. So what this does basically is that it sets up the camera in a dictionary format, the camera images in a dictionary format. So we're going to create this data dictionary, and under image, we're going to have all the images saved. Now, basically what we're doing here is, first of all, we are getting the image raw data, and then we are reshaping it with the NumPy, because we need the data dictionary to be set up in a certain way so that later we can uh, use those data and render it on a window. So what we are basically trying to do here is we want to look at what the camera is looking at. We want to get the live streaming of the camera from the vehicle, not just save image by image or frame by frame in our local directory, but we want to look at what the camera is looking at in real time. And for that, we are calling this camera callback function. It is actually directly from the CARLA documentation. So if you can find this function directly in the CARLA documentation, just copied it from there. What it does basically is it reshapes the raw camera images according to this dimension, right? So we have actually 6 dimensions here. So the first dimension is the height of the image, right? So the height of the image. The second dimension is the width of the image. So that basically tells you how many uh, pixels you have along the height, how many pixels you have along the width, and then you have these 4 more channels added to them, basically color channels. So you have the red, green, and blue, 3 color channels, but you have 4 here. So what the other one is basically for transparency, which we call alpha. So there's R, G, B, and alpha. So the alpha is basically the transparency of that particular pixel, meaning like, how much can you see through that particular pixel to the next object. So that's how we are reshaping each of the images or frames using the camera callback function. So I'm just going to run this cell here, and then I'm going to copy uh, some other lines directly here. So what this basically does, it calls in the get attribute method of the camera blueprint, the blueprint that we are using, the RGB camera. And then it configures the size of the image, basically the width and height of the image, uh, and that has an opposite way of saying. So if you have the x time along the x dimension, it actually goes through the width, and the y dimension is for the height. And then we are gonna initialize this data dictionary by saying camera data is equal to image, and then we are gonna initialize it with all zeros of the same dimension of the dictionary that we just showed here. So we need the image height, we need the image width, and we need 4 channels for R, G, B, and alpha. And we are initializing this dictionary with all zeros. And then we are gonna again go back to the camera.listen method. We're going to call it the lambda function that is going to work on the image files that we're going to get from the camera. And then we're going to save each image. We're gonna give each image to this camera callback function. And then we're going to give it the camera data dictionary, the dictionary that we just initialized, right? And then each time what this will do is it will add the image to the dictionary, right? And then we can render that image by calling in that dictionary again, and we can put it on a window where we want to observe it. So let's okay. So the camera trying to operate on a destroyed actor, because we just destroyed the camera, right? So let us go back and open up the camera one more time. I'm not sure if we still have the vehicle though. Okay, we see that the vehicle is waiting here. What I'm gonna do is I'm gonna destroy all the vehicles so our roads are clear. So I'm gonna do vehicle.destroy. Um, but what this is gonna probably do is it is trying to, okay, the vehicle has already been destroyed. Hmm. Mhm. Okay, so let us do one thing. We want to destroy all the vehicles that we have. So I'm gonna type in for vehicle in world, and then I'm going to use the getActor method. Get actor, get actors, and then I'm gonna filter for vehicle. So filter for vehicle, and then for each vehicle, I want to destroy it. All right, so you see that the vehicles are gone here. As soon as I ran the command, the two vehicles are gone. So what we basically did is we ran a for loop with the vehicle.destroy method, and we looked through all the actors that we have in our world and all the type of actors that are vehicle. How about we do the same for camera as well, because we just ran a camera. So what we're gonna do is we're gonna change vehicle to cam, and then this one we're gonna change to sensor, and then we are gonna destroy all the sensors as well. Done. So whatever sensors or camera or vehicle we set up before, so that should not be an issue anymore. So we should be able to set up our vehicles one more time. So what we're gonna do is we are gonna go back to this piece of cell and we're gonna run it. So we just brought back the vehicle here, as you can see. And then okay, we're gonna set up the camera because we just tried all the sensors, right? So we're gonna set up the camera. Yeah, let's set the vehicle on autopilot. And then we already ran this piece of cells, but let's just run them again. And then this, okay, all right. So this was just to destroy the vehicle, right? So I'm gonna put this up. Yeah. So if we need to use it later, we can just copy it from there. All right, so right now we are listening to the camera, and we need to render whatever we are getting from the camera on a window. And for that, CARLA actually has this nice piece of code snippet that you can use. I'm just going to copy it here. So what this basically does, it's imports. So first of all, we have imported CV2. So it opens up a window, named window with the name RGB camera. And then based on the type of camera we are using, we're automatically sizing it. So we have this CV2.window auto size method. And then we are going to show whatever the camera is looking. So we're seeing. So we are going to use this cv2.imShow method. We're going to put it on the RGB camera window, and we are going to render the data that we got in this camera underscore data dictionary, right? So this is our camera underscore data dictionary. So, and yeah, so we are rendering it in this window, and then we have this wait key just to make sure that we have time to render this before the window shows us an error. And then we are gonna do it continuously. We are gonna continuously we continuously want to render these images. So whatever we are showing here, this only works for one frame, right? But we want to keep this loop going without any I mean, without any pause. So what we are going to do is we're going to set up an infinite while loop, and then we're going to put this line inside the while loop CV2. I am sure that it's gonna continuously show us what the camera is seeing. And then we have this piece of line where we basically say that if we hit Q from our keyboard while looking at the camera window, then it's gonna break the while loop. So that's how we destroy the camera view. And then after that, we destroy all the windows so that it does not create an issue for the later pieces of code that we're gonna run. So let's just run this cell. And you see that as soon as I hit enter, this new window popped up. And if I click on this window, uh, this is what we are looking at. So you see that the vehicle is driving and we are exactly seeing what the camera is seeing. So this window is giving us whatever we're seeing, but we don't know where the vehicle is. Let me see if I can find it for you. Well, oh, there it is. Yeah, so we have the vehicle there. So you see that the vehicle is here, it's operating on the road from this location. And yeah, so the vehicle stopped there right now, and that's exactly what we're seeing in this window, right? So that's how you set up the camera. You get the live view of the camera. And if you point your cursor, if you click on this window, on the RGB camera window, and then if you press Q on your keyboard, then what it does, it destroys the camera immediately, right? So it destroys the camera and the window. Oh, I'm sorry, it does not destroy the camera, but it destroys the window while we are rendering the images. But that's how we do it. And now let's okay, let me yeah, I think that's pretty good enough. All right, but there are other different types of camera you can find. So there are DVS camera, there's optical flow camera, instant segmentation, semantic segmentation. There are many different types of camera available on CARLA, and you can get all of those from the blueprint. But for now, we are gonna move on to the next sensor because we're short on time here. So we're gonna look at LiDAR and radar together. Again, all right. So we're gonna do the LiDAR and radar. So right now we need to install two more packages before we move on. So we are going to do pip install. First of all, we need the 3D visualizer because whatever we visualized with the OpenCV that works for a two-dimensional camera, it does not work for 3D visualization. So we need a different package, which is called Open3D, to be able to visualize the LiDAR point clouds. And then we need matplotlib for some operation because LiDAR is going to have a point cloud and we need to plot that in the 3D visualizer. So I already have these packages installed here on my computer, so I'm not going to run this cell. I'm just going to move on to the next cell. And then again, we're gonna need to import some packages. I'm just gonna copy and paste it here. So just like before, we're importing CARLA, we're math, and then random, time, NumPy, we're importing as NP, and we are importing the 3D visualizer as O3D, and we are importing the matplotlib as CM. All right, and then I'm gonna hit this cell. So all the packages have been imported. And now what we're going to do is the first thing is we set up a client server side, right? But I think that's already set up. We are already talking to the server, so we don't need to set up the client. We also have set up this blueprint library and the spawn points here, so we don't need those things. We have a vehicle running on the road as well, so we don't need we did not destroy the vehicle last time. So the vehicle is still operating on the road. That's fine. What we're gonna do is we're gonna put a LiDAR and a radar on the vehicle that already exists there. But while we have this vehicle operating on the road, we would like to have more actors on the road, maybe more vehicles, right? So because when we're using the LiDAR and radar, what we are basically going to see is that where are the different obstacles. Now, some of the obstacles are going to be static. So those are basically your building, trees, your road infrastructure. And then some of the obstacles are going to be dynamic. They will be moving. So those will be like other vehicles and pedestrians, right? And that's going to help us understand the point cloud, how the point cloud works, how it looks, how it differs from the static objects to the dynamic objects that are moving, right? So what we're going to do is we are going to import a couple of lines here um, that's gonna spawn 100 different vehicles at random spawn points. So as you can see, so again, we are running this for loop 100 times, and we are getting 100 different vehicle blueprints, and we are randomly choosing them from the blueprint library by using the blueprint library dot filter, and we are filtering for vehicles. And then we are trying to spawn those vehicles on our CARLA simulator map. So basically, we're using just as before, we're using word or try spawn actor method. We're giving it the vehicle blueprint and the random choice from the spawn points. Now, I did from one here because our vehicle was at the beginning, it was at the zero location. So that's why I did not put zero here, but I think we can take it out. We don't need this anymore. So if you already have a vehicle, you cannot spawn another vehicle there, but that's fine as long as you use the try spawn actor method. You will not get an error that will stop your code because it's going to try to spawn the vehicle there. If it does not, it tries in another point. And then for all these 100 vehicles that we are just going to create with this for loop, we want to set them up all on autopilot so they will move automatically. We don't have to control them. So we have this another for loop. Basically, what we're doing is we are using the world.getActress method, and we are filtering it for all the different vehicles that we have. And for each vehicle, we are setting them up on autopilot. So I'm going to run the piece of code here. So you see that as soon as I ran the code, different number of vehicles appeared. A Tesla Cybertruck is there, a fire truck is there. We see a Volkswagen minivan, uh, and probably this is our vehicle, the Lincoln MKC. And there are so many different vehicles operating on the road, right? So there will be 100 different vehicles, actually 101, including our vehicle. Now, after this, we are gonna use some boilerplate code directly copied from the CARLA documentation. So what this does is basically it sets up the LiDAR configuration and the Open3D visualizer. I'm sorry, not the LiDAR configuration. This is for the visualizer, the 3D visualizer configuration. So we are configuring the 3D visualizer configuration. We are setting up the range for the windows, the color map that it is going to use, and we are gonna initialize the different variables here. So we're gonna use these different methods here and initialize with uh, some numbers to be able to get the rendering window. All right, and we're gonna just run this without any sort of changes. You might get some warning here, but that's fine. It's just some version issues, so it's not a problem. That's not gonna stop you from the next couple of steps. All right, and then we are gonna put this uh, two functions. So just like before, so what we did for camera is we created this camera callback function where we are saving all these different images in a data dictionary, right? And we're going to do the same for the LiDAR and radar, but it's going to be a little more complicated than before. So we have these two callback functions, one written for the LiDAR callback, another one written for the radar callback. Basically what we are doing is we are getting the LiDAR point cloud data, and then we are setting it up in this dictionary that we are calling the point list. And we are setting it up in a way so that our Open3D visualizer can look through it. You don't really have to we don't really have to go line by line through this code. But there's a link where you can find the explanation for this. It's prepared by the CARLA developers. I can show you. It should be on YouTube. So if you go to this video, it's an in-depth look into CARLA sensors or something. So you see that this particular video, an in-depth look at CARLA sensors. So this is where you will get these particular boilerplate codes, where you can basically set up your 3D visualizer for both LiDAR and radar. So feel free to go through this, although I don't think they explain all these lines. But this is something that you will not need to change. This is a fixed uh, set of codes that you just need to do for the visualizer to be set up, right? All right, so very, very similar lines here for both LiDAR and both radar. But the thing that is interesting here that I want to talk about is you see that there are four channels again for LiDAR. And basically those are your X, Y, Z, and your I think the relative speed, if I'm not wrong. So those are the four, or the speed. So those are the four variables. Um, and again, here for radar, you have the same, you have the X, Y, Z, and the detection of the velocity, because that's what you can do with radar. You can detect where an object is, how far it is, and what is the relative speed with respect to your location or your position, right? So that's what we are doing here. We're using the LiDAR callback and the radar callback functions. So I'm just going to run this piece of cell here. And then before we are able to see the LiDAR and radar data, we need to configure the sensors itself. So I'm going to copy some LiDAR and radar configurations here. So that's going to set up your different attributes. So you remember we used the set attribute function for camera 2 before. And we are using the same method, but this time for LiDAR and radar. This is basically setting up the camera and the type of LiDAR and radar we are using. So you see that the first line, we are finding the blueprint that the ray we are using the raycast LiDAR. There are a couple other different types of LiDAR in CARLA. Feel free to play around with them. And then you have these these different attributes basically configuring what your sensor can do, right? So how much noise you can have in your LiDAR, if you can change those based on your real world values. Uh, what is the how many different number of channels you want to have, what should be your rotation frequency, because LiDAR uses a laser and then it uses a motor to rotate the sensor, the laser continuously. So each time the laser hits an object, it can detect that there is an object and how far it is. So this rotation frequency is basically telling you how many times it rotates every second. So it will rotate 20 times per second. And then points per second. So how many points you want to record. So right now we have about 500,000 points. So it's going to record 500,000 points per second. It has the range, set of the range. So it is going to be able to see up to 100 meter on the road. And then we do check if this is 100 meter or 100 feet, I forgot. And then once we have configured the LiDAR, just as the camera, we need to set up the LiDAR on the car, right? So we have this LiDAR transform variable where we are basically telling it the location of the LiDAR. And just as before, uh, what we did for the camera, we are doing the same thing here. We are using CARLA.transform method, and the point is we are assigning the z coordinate to be 2. That means that once we attach it to the vehicle, it's going to be 2 meter from the vehicle center of gravity. And that's what we are doing. So we are spawning the LiDAR, just like the camera and the vehicle. We are using the spawn actor method. We are using the LiDAR blueprint again, and we are using the location of the LiDAR where we want it to be set up. And then we are using the attach to argument and set it to vehicle so that it attach the LiDAR to the vehicle. Doing the same thing for radar. Again, you have to look for the blueprint. You have to set some attributes, and you can change those attributes, of course, depending on your need or the type of sensors that you are using in the real world that you want to simulate. You can set up the transform, CARLA.transform, CARLA.location is equals to 2. So it's gonna place the radar 2 meter from the 2 meter above from the vehicle center of gravity. And then we are doing the spawn actor. We are attaching it to the vehicle. All right, and then this is basically the list of points that we are getting from the LiDAR and the list of points we're getting from the radar. So it's basically just the initialization of the dictionary that we are going to use. So that's why we do not have any values here. It's just we're using the method to set up the list, initialize the list. And then the list is going to be populated using the data that is coming from the sensors, the LiDAR and radar on the vehicle, right? So just as before, what we did with the camera, we're doing the listen method. So lidar.listen and radar.listen, and we're using the lambda function. And whatever data we are getting from there, we are sending it to the lidar callback function, and the lidar callback function is going to put it on the list. So the point list is going to be our point clouds, and the radar list is going to be our radar measurements. All right, and then as soon as we hit this, know that your LiDAR and radar has been set up, and you are listening to the LiDAR and radar right now. But because you do not have any rendering windows set up, so you are not observing anything yet. So just like the camera, we need to set up a window with the Open3D to be able to see whatever the LiDAR is seeing, right? And for that, we are gonna put this few lines of code again. So what this basically does, it sets up your Open3D visualization window. It gives a name to the window, CARLA, LiDAR, and radar. It sets up the width and height of the window and the left and top coordinates of the window. And then it renders. So how should we render, right? So it sets up the background colors, it sets up the point size, it sets up the coordinate frames and so on. And then we have this while loop. Definitely we need a while loop, and we need to set it to as an infinite while loop unless we stop it manually. And we want to continuously render the frames that we are getting from the radar and the lidar, right? So this is basically doing that. And then we put a time.sleep here because it takes a little bit of time to render, because it's basically getting the data from the vehicle sensor and then casting it on the window with the Open 3D visualizer, right? So it takes a little bit of time. And if your code does not stop, or if it does not wait until it is rendered, or it has been streamed, the current frame, and it is trying to move on to the next frame, then it creates a collision, and then you're gonna get an error. So that's why we have the time.sleep here. And then every time we are increasing the value of frame by 1, just to keep account of how many times we have done this. And then once we are outside the loop, we are just gonna stop the lidar. We're gonna destroy the lidar. We're gonna destroy the radar and everything. And we also have this couple of pieces of lines, just like before, to make sure that we have taken out or destroyed all the actors. Actually, I'm gonna take out this couple of lines from here, and I'm gonna put it on the next cell. So let's run this one. So as soon as I run this, you see that this window popped up here. And if I can show you this window, so you see that the lidar has started recording. So wherever my vehicle is on this map, this is the view I'm getting from the lidar. So you see that the vehicle is moving, so the objects are moving as well. You can see that the objects are passing by. There's something round here where the vehicle is moving. So the vehicle, if we understand it correctly, it's taking a left turn right now. And then, yeah, it's operating. So the green dots that you have, we have set up the color maps in a way so that whatever the orange, red, these colors you were watching. So yellow means it's closest to the vehicle, and then the more it get orangish or reddish, it means it's far away from the vehicle, right? So the color map is set up like that. And then the green dots are basically your radar measurements. So the radars, I mean, what do you call it? The window of view, right? So the radar's frame of view is like this. And this is all the objects, different objects are coming up here. So you see that there's probably some obstacle there. That's the vehicle is closing in that, and probably it's gonna take a turn from there. Yeah. So that was probably a building there, and then it took a turn again. So that's how it goes on. So that's how you render your lidar and radar data. So the lidar is basically the point cloud, and the radar is the green or the bluish dots that you are watching here. So those are your radar measurements. So I'm gonna destroy uh, the window just by shutting down the kernel here. We don't need it anymore. Mhm. And I'm gonna show you one critical thing that I personally felt that I think it's so what happens is that because this is a server and it runs on a particular port, so if you because many times you might need to shut down your kernel and restart the code and run a couple of lines again, right? So what happens is that if you already have a client set up with your server, sometimes the port is busy, and if your port is already busy, you may not be able to communicate with the CARLA, and that will give you an error. So the way to fix that is that you go to your Windows PowerShell, and then you just use the netstat command with the ANO option, and then you are looking for the string 2000 because that's what the port CARLA uses, right? So CARLA uses the port number 2000. So you use this command in the command line interface or in the Windows PowerShell netstat ANO and then find string 2000, and it's going to tell you which process it is working on, the CARLA, right? So right now we are saying that the CARLA is using this particular process ID. So if I close my window here and rerun the find string, you see that nothing came up because I just closed down the server, right? But if my server is running and I'm trying to set up another client, sometimes the port is busy, then it becomes difficult to. The reason is I have already set up this client from this computer, right? So if I want to use the same computer to set up another client. So sometimes I might get an error because the, the IP locations are the same. So what you need to do in that case is you need to look up the find string. You need to look up the process ID using the netstat command. So this is basically your process ID 43728. And then once you found the process ID, you basically need to kill it. So you use the task kill command followed by PID, the process ID, and you need to type in the process number you can see there. So you need to type in 43728, whatever process number you get here, and then followed by the / and F, and then you hit enter. So you see that we got an error. The reason is the process is not there anymore because we already closed down the server window and we ran the netstat command and we did not get any more process right after closing down the server. And that's why we are getting an error when we are trying to kill the process. But as long as you have the server running and the port is busy and it's listening to something, you can always kill that task to be able to connect to the server back again from your personal computer. So right now, just wanted to share this piece of information with you so that it helps you operate smoothly with CARLA. So I'm going back to the CARLA root directory, um, CARLA uv4.exe. All right. So we are running a little bit over time here. So what I'm gonna do is I'm gonna stop our workshop here, and we are gonna come back at 1:30 after lunch. And then we're gonna talk about one more important thing, and that's going to be regarding how we can let me see how much we have to cover. Um, mhm. Yeah, I want to show one more thing before we move on to the rest of the workshop, the next sessions. So I would like to show you the how to set up an autonomous vehicle controller with CARLA. So bear with me for 10 more minutes, and then we are gonna go into the break, and we're gonna come back at 2 o'clock. But I think I can finish this session within next 10 or 15 minutes. Okay, let me share my screen one more time. Okay, and then let me go back and oh, I think I already opened the server. The server is running here. Here is the server. And then the next part, what we are going to do is let us restart this kernel. Restart the kernel and clear all outputs. And we are going to put another new section here, and we're going to say longitudinal control of vehicle. So before we set the vehicle on autopilot, so now we're going to see how we can control the vehicle autonomously, right, by ourselves. All right. So again, we're going to import some files, some packages. So we are going to import the CARLA, NumPy as NP, and CVDO and time. And then we're going to set up a communication with the CARLA server, just like before. We have this client, CARLA.client. We have the world variable set up for the client get world method. And then we have the blueprint library. So basically, we are getting the blueprint library for this particular world from the world.get blueprint library. And we're going to run this piece of cell. And then we are going to spawn a vehicle for us, right? So we need some spawn points, just like before. We got some spawn points on the current map that we are on, using the dot get spawn points method. And then we need to get the vehicle blueprint first before we can spawn it. So we are getting the vehicle blueprint from the blueprint library using the same vehicle as before, link on MKZ. And then we need to spawn the vehicle. So that's what we are doing here, trying to spawn it, try spawn actor method. of the vehicle blueprint in the spawn points, and then we are setting the vehicle set autopilot method to false because we want to operate it ourselves. Okay, so right, so once we have run it, let's find out where our vehicle is. Let's see. Okay, it's there. So there's our vehicle. And now what we're gonna do is we're gonna set up a controller. So if you have a control engineering background, then you most likely know about the PID controller. Um, so it's basically a proportional integral derivative controller that works that works to minimize error that you are trying to track. So if you have a reference trajectory or if you have a reference speed that you want to follow, you can use any controller to do that. So basically the controller tells you how you should change your throttle, your steering to be able to achieve your desired trajectory, right? So when as human drivers we drive, say our speed limit is 45 mile per hour, we do not just hit the gas pedal all the way down and trying to hit speed limit 45, right? So what we do is if we are at a stall condition, maybe we are hitting the gas pedal and then we're trying to ramp the speed up. And then once we hit close to 40 mile per hour on a 45 mile per hour speed limit road, we try to be gentle with the gas pedal, right? Because we don't want to put more gas into it and then cross the speed limit. So that's exactly what a controller does. So if you want to track a particular speed, say speed limit 45 mile per hour, maybe you are going from 0 mile per hour all the way to 45 mile per hour. But the transition needs to be smooth, and it needs to be smoother as you close in to the desired speed or the reference velocity that you want to track. And that's where the controller comes in. So the controller takes care of that need that you need to slow down as you close to your reference speed or desired speed. You need to be more gentle on the gas pedal, right? Maybe and as soon as you have hit 45 mile per hour and you went above 45 mile per hour, maybe 46 to 50 mile per hour, you need to hit your brake to slow down your vehicle back to 45 mile per hour or lower, right? And that's what the controller does by itself. So it basically tracks the error. So how far you are off from your desired speed or your reference speed, and based on that error, it tries to determine how much what should be the amount of throttle or brake or steering you need to apply to your vehicle. So here we have the PID controller setup. Just trust me on this. So this is how we have set up a PID controller, but feel free to play around with it. Feel free to play around with the different values of the controller, like the KP, KI, and KD. So those are basically the controller gains, depending on the error that you are recording, with respect to the desired velocity or trajectory. So those are proportional, integral, and derivative gains for your controllers. So you can play with the numbers and you can see how it changes the vehicle's performance while you are tracking the speed. But for now, we're just gonna hit Shift Enter. And the next function is get speed mile per hour. It's a silly function just to convert the vehicle velocity from mile per second to mile per hour. And because this is a 3D world, so what we get is the velocity. We get it as a vector of three components, the x, y, and z components. So we need to do this operation to be able to find out the speed from these different speed components. And then we are converting the speed from mile per second to mile per hour using this conversion. All right, and then what we're gonna do is we're gonna put this piece of code here. So basically, I showed you this code earlier. So what it does, it sets up a fixed spectator view. So it makes sure that you are always sitting right behind the vehicle, tracing it as it traces the route. So as soon as I hit enter, you will see that the spectator view has shifted, and we have a particular spectator view. So you see that we just stepped a couple of steps back, and now we are looking at the vehicle. It's just like a game view setup. So I played around with the different numbers here to be able to get this view, but feel free to play with the numbers yourself based on what view you like most. The next is we're gonna set up a camera just like before. So we already went through all these steps in the previous uh, couple of cells. So we're just setting up a camera blueprint, defining a camera callback function, and then we are listening to the camera. And once the camera is ready, we're just printing camera is ready. So our camera is ready now. And then I'm gonna put this piece of code here that's gonna help us track the speed. So what this does is that the first two variables we have here are target mile per hour. So you need to give a particular target here, 10 mile per hour. Let's set it to just 5 mile per hour. I want it to be very slow so that we are able to see before it hits any object, because we are not going to apply any steering command right now. So what's going to happen is the vehicle is going to try to go straight along the road, right? So it does not have any knowledge whether there is an obstacle in front of it, or whether there is the traffic light is changing from green to red or yellow or whatever, or if it's going to hit the car that is in front of it. It does not have any knowledge. To be able to have that knowledge, you either have to run it on the autopilot mode of CARLA, or you need to develop your own machine learning model from where you can understand the road geometry and whether there is a vehicle or something you're about to hit. And based on that, you can apply the steering as well. But for now, we're just going to focus on the longitudinal control for this workshop. Uh, all right, so, and then the next thing we have here is DT. So this basically gives the fixed delta seconds. So what it does is there are two modes in CARLA. One is the synchronous mode, and another one is the asynchronous mode. So if you can understand this, so what happens is that when the server is running, it runs at a particular speed, right? So depending on your machine's capability. But when you are simulating this world, you are simulating at a particular frequency, and that frequency can be different from your real world frequency. So what the synchronous mode does is that it kind of tries to align this to time frame so that you have a more stable timing. So this is a recommended practice when you are working with the controllers. So you can set it to the synchronous mode so that your real time and the server running time matches. And then we are setting up some values for the KP, KI, and KD. Feel free to play around with these values, change them, increase them, decrease them, and see how it affects the controller and how the vehicle tracks the speed that you just set here. And then we are opening up this CV2 named window because we want to see what the camera on the vehicle sees. And then we have this for loop. It's basically to add some sleep time before we start on the next steps of the code. So basically what we're doing is we are comparing the current speed and the target speed. We are getting the error here as E, and then we are giving the error to the PID function that we created for the PID controller. And based on that error, it's gonna try to find out what's going to be the required amount of throttle or gas that we need to put on the vehicle to be able to track the speed. So using the U is basically the control value. U is the control input. So based on the control input, we set up some min-max limit because we don't want to go above some certain limit when you are controlling the vehicle. As you know, you can only have a certain amount of acceleration for a particular car, right? You cannot go above that acceleration no matter how hard you are pushing on the throttle. So this is basically that, setting up a upper limit and a lower limit for your throttle and brake respectively. And then we are going to apply the control. So once we have the throttle and brake, and if we had steering here, which we don't have here right now, we have the no steering command here for now, then we need to apply that control to the vehicle. And the way to do that is you use this vehicle.apply control method. And then inside that you do the CARLA.vehicle control method. You give the throttle value to the throttle value. You give the steering value to the steering value, steering argument, and then you give the brake amount. And the rest of it is just to set up the CV2 window so we can see whatever the vehicle is seeing through its camera. And then we have this piece of code here just to be able to intervene when the camera is running and the vehicle is operating. So if we hit Q on our keyboard, it will essentially destroy the camera and we will come out of the while loop here. And after that, we just need to remove everything that we have. So we are going to stop the camera. We're going to destroy the camera. We're going to destroy all windows in CV2, and we're going to destroy all the vehicles that we have. We are going to destroy all the sensors, and we're going to print, done, clean up. All right. So right now, let's just run this piece of cell. As you can see, the vehicle started moving, and we have this window popped up here. Where we can see the camera view of the car. And you see that the target speed is 5 miles per hour. We are exactly tracking it at 5 miles per hour, but it's going to crash it here because the vehicle does not know that it's going to crash onto this museum, right? So it's going to go there and crash onto it. And the speed has turned to 0 miles per hour. So that's how we do it. So that's it for today. I mean, for the hands-on demonstration. And the next session, we are gonna come back at 2 o'clock exactly when we are gonna give you a particular problem that you are gonna try to solve on your end. But because I know that it was very hard to follow and do it yourself at the same time when watching me through Zoom, so what I'm going to do is I'm going to share the script that I just wrote here with you on the chat. So please keep this script uh, for your record so that later you can come back to the script when you are watching the recording and you can get the entire script that we just did together. So I'm going to put this IPYNB file in the chat here for everyone. Please feel free to download it and keep it for your record. And I would recommend before our 2 o'clock session, if you have time, please go through the script and try to run the cells by yourself on your local machine because that's gonna be the most effective way to learn from the workshop. If you can try and do those things by your own on a local machine, then you'll learn the most. So if you have any questions, once we come back at 2 o'clock, we have a discussion session from 3 o'clock. So we're gonna do discussion on any of the issues that you faced, or if you have any questions for me. So for now, you can sign out, and we're gonna sign back in at 2 o'clock after the lunch. Thank you very much. So Dr. Karimuddin, I'm gonna pause the recording on my end for now, and when we come back, I'll start the recording again. I see that Kuram had a comment on the chat. He's saying that can we get the recorded session? If yes, can you please share in this email address? So what I'm gonna do is because I recorded it in the cloud. So as soon as I get the recording of this first part of our workshop, I'm gonna share it in the chat here. I'm gonna keep this Zoom window open. So the Zoom meeting will be open. But as soon as I get the recorded session available on Zoom, I'm gonna share the link on the chat so that you can have it for your record. And then right after we have the next session, I'm gonna do the same if we have some recording to share. Thank you. So I see that there were two questions from Masha and Grace Schneider. So Masha was asking, can we also change the orientation of the camera? Absolutely. You can change the orientation of the camera, and the way to do that is by CARLA.rotation. So what we showed you guys on the during the demonstration or the workshop today is basically we were changing the CARLA.location. If you play around with the CARLA.rotation, then and the variables within CARLA.rotation are pitch, roll, and yaw. So if you change or play around with those numbers, pitch, roll, and yaw, and then you will be able to change the orientation of the camera. The next question is from Grace. Thank you, Masha. Um, and then Grace was asking, is the process for a LiDAR sensor similar to a camera? It's very much similar. I mean, the setting up the LiDAR, getting the blueprint, spawning the LiDAR sensor, those steps are very much similar. But as you have seen, for LiDAR and radar, the configuration is a little more, it takes a little more effort to configure the LiDAR and radar and to be able to render it, because you basically have the in images you have the 2D space, but when you are working with the point clouds, you have a 3D point cloud. So it's more difficult to render, and we need a specialized visualizer, the Open3D, for that. So otherwise, it's the steps, the processes are very much similar. I mean, it's the same process that we follow for camera to be able to get the images and render it on a window. It's just different because of the data. I hope that answered your question. All right, so stopping here for now. I will be back at 2 o'clock, and as soon as I have the recording, I will share it in the chat for you. Thank you. All right, welcome back again. So before I state, so I have two challenges, simulation challenges for you to try out on your end, based on definitely what we discussed in today's workshop in the morning. So before I state the challenges, please feel free to let me know if you ran into any issues or if you want to discuss anything that you need further clarification on. So please feel free to unmute yourself if you have any issues that you would like to discuss, or if you have anything that you would like me to clarify. Also, feel free to post your questions in the chat if there are any. Okay, if there are no questions for me at this moment, that is fine. So let me state the two challenges that I'm gonna give you right now for this part of the session, where you can try on your end to see how you can do that part of the simulation that we are stating here. So the first thing I would like you to try on is to set up a different camera. So we already showed you in the morning demonstration how you can set up a camera sensor, particularly placed at the front of the vehicle, right? So we showed that uh, after you get the camera blueprint here for the RGB camera, you can get the camera attached to the vehicle using the argument called attach to vehicle. And then any transformation or any coordinate that you give it to the function, or if you give it to the var.spawn actor method, so that coordinates are going to be converted in terms of how far it is from the vehicle center of gravity in terms of longitude, latitude, and altitude. So basically, this is what we did in the morning demonstration. We placed a camera at the front of the vehicle, 0.4 meter offset from the center of gravity in the longitudinal direction, and 1.6 meter offset from the center of gravity in the altitude direction. Now, what I would like you to do on your end is try to see if you can find a way to place a camera at the back of the vehicle. So basically, what I want you to try is to set up a rear view camera where you will look at the rear side of the vehicle, and you will record those the camera captured images in a particular folder. So you can create a new folder. Here I did the front camera images. You can create a rear camera images folder, and you can save your TNG files from the images that you can capture with the camera in that folder. So that's the first challenge, to set up a rear view camera. And also feel free to to play around with other orientations, locations, to see if you can set up a side view camera as well. And when we come back at 3 o'clock to discuss these challenges, we're going to tell you how to do that, how to set up a rear view camera, and if you'd like to set up a side view camera, how to do that as well. So that is the first challenge, setting up a rear view camera. The second challenge that I would like to give you is to play around with the controller. So in the morning demonstration, we showed you how to set up a PID controller to control the longitudinal motion of the vehicle, right? So we showed that using the PID controller, you can get the control input, and from that, you can basically set up an upper limit and a lower limit for your throttle and brakes, respectively. What I would like you to do is, instead of using the PID controller here that we already set up, can you design a rule-based system by yourself to operate the vehicle longitudinally? So what I mean is, you can think of it when you are driving the vehicle, right? So you're driving the vehicle, you are targeting to reach a particular speed when you're operating. And if you are too far behind from the speed you are targeting, so say, for example, you are at 10 mile per hour, and you want to reach the driving speed of 45 mile per hour, you would like to press the gas hard, right? So at the beginning, you will press the gas hard to kind of accelerate your vehicle. And as the velocity or speed of your vehicle goes up, 10 to 20 mile per hour, 20 to 30 mile per hour, and then essentially, as you are closing into your target speed, you slow down your vehicle, you go gentler on your gas pedal or throttle, right? And eventually, if you cross your target speed of 45 mile per hour, what would you do? You would press the brake, right, to slow it down, to make sure that you can track 45 mile per hour speed limit without going too above the speed limit of the roadway. So what I would like you to do is try to see if you can set up a rule-based system here. So you can try with loops, you can try with if else conditions, uh, and try to see if you can set up a very crude controller without going to maybe a PID level controller or a model predictive controller level controller. Can you set up a controller by yourself using some logics and some rules that, okay, whenever you are over, maybe when you are very close to within 5 mile per hour of your target speed, maybe you can put a less value in your throttle. And if you are above the posted speed limit of 45 mile per hour or a target speed, then you can try to slow down the vehicle a little bit, right, by pressing the brakes and so on. So that's what I would like you to try. So that's the second challenge. Try to develop a very crude self-made controller by yourself. It can be a rule-based system where you are posing some conditions that when you're above this speed, slow down by pressing the brake, or when you are too far off the speed, you can press the gas to accelerate. So those are the two challenges that I would like you to try on. So again, just to summarize, the first challenge is about setting up a rear view camera. And the second challenge is developing your own rule-based system for controlling the longitudinal motion of the vehicle. And we are gonna connect back at exactly at 3 o'clock. So you have about 50 minutes to try out these two particular challenges that I just mentioned. But I'm here. I'll be here in the meeting muted. So if you have any questions in the meantime, please feel free to unmute yourself, and I'll try to address your queries. Thank you. So Peng, just saw that you just joined now. I don't know if you heard about the challenges or you missed the part. So just to summarize it for you one more time. So the two challenges I gave to the audience is first is to set up a rear view camera. So we showed how to set up a front view camera. Try yourself if you can set up a rear view camera in the same way. Play around with the rotations, with the locations, and see how what to do to set up a rear view camera. And the second thing is we use the PID controller to determine the value for throttle and brake. For longitudinal motion, I would like you to try if you can set up a controller by yourself, which can be like a rule-based system where you are basically posing conditions on the vehicle, whether to accelerate or to brake, depending on at what speed you are operating at and what speed you are targeting to operate. So those are the two challenges, and we'll talk about the solutions and the challenges that you face along these problems at 3 o'clock. Thank you. Okay. Okay. So, hi, welcome back again, everyone. So, I hope you had a chance to test the two challenges that we posed towards you. So please let me know uh, if you want to share your screen to show your solution. That is absolutely fine. I can enable screen sharing for you. But please let me know if there's a participant who wants to show your solution and how you solved it. It would be a great learning for all of us. Anybody wants to volunteer? Or if you, while trying out the solution, if you have faced any issues with the challenges, let me know so we can try to resolve it together. Any questions for me? Okay. If not, then what I'm going to do is I'm going to quickly show you how how we could solve the two problems that we placed in this session. So the first one was how we can set up a rear view camera, right? So we talked about in the morning session how to set up a front view camera. And the first challenge was can you tweak the parameters so that you have the camera facing the rear side of the vehicle, like a rear view camera. So let me share my screen one more time and show you how we could do that. Once again, I have to run my CARLA server. So I'm going to my CARLA root directory, which is in my C drive here, and I'm running the CARLA server. Okay. So once the server is up and running, then we can use this script to set up the client side of the server. The client side of the software, and then we can communicate with the server to operate on the world, the simulated world, right? So I'm still waiting for the server to open. Okay, it's running right now. So here on the left side, we have the server open and the simulated world in CARLA. So let me go to, so this is the same script that we used in the morning session where I showed you how to do the route planning, the CARLA sensors like camera, LiDAR, and radar. And also we talked about how to do the longitudinal control of a vehicle autonomously, right? So the same script. So I'm going to edit this script as I shared this with you in the chat, and I'm going to show you how to do the rear view camera setup. So once again, we start from the package import. So we are importing all the packages that we need for the camera sensor. Again, we are setting up the client to communicate with the server side. And then we are collecting the blueprints where we're setting up some spawn points where we can place the actors like vehicles, pedestrians, and so on. And then here, this part, this line I have commented out. So this was the front view camera setup, right? So we had the CARLA transform, CARLA.location x equals to 0.4 and z equals to 1.6. So basically, these two coordinates are the offset amount from the vehicle's center of gravity. So if we uncomment this line, what this will do is this will place a camera 0.4 meter uh, in front of the center of gravity and 1.6 meter above the center of gravity uh, while being attached to the car, right? So right now we need to set up a rear view camera, and the way we can do that is basically, so you can think of it, the camera is looking at the front side of the vehicle, right? So if you want it to look at the back side of the rear side of the vehicle, you basically need to turn it around, right? So you take the camera and you rotate it by 180 degree, and then it points towards the rear direction of the vehicle, right? So that's exactly what we are doing here. So we are just changing this script inside the CARLA.transform method. We are placing, we are posting the location as x equals to minus 0.8 because before we placed the camera at the front, now we are placing the camera at the back side or the rear side of the vehicle. So that's 0.4 meter was for the front camera, center of gravity, offset from the center of gravity in the positive direction. Now we need to go to the negative direction for the rear view camera. So we changed it to minus 0.8. So that will basically take the camera at the rear side of the vehicle. And then we kept the same altitude or the offset from the center of gravity, the same amount of offset, uh, which should work. But we can change these numbers, of course, if we see that we need a better view, we can adjust these parameters to change the location of the camera. But more importantly, what we need to do is we need to turn the camera 180 degrees so that it is then pointing towards the rear direction of the vehicle. So that's why we have this additional part here added. So where we are adding the CARLA dot rotation method, and we are putting the yaw value to have a 180-degree rotation with respect to the axis that goes upward, right? So it will turn or rotate the camera 180 degree and basically pointing it, making it point towards the rear direction of the vehicle. So if we run this shell, or sorry, if we run this cell, so let us, it's saying that the vehicle is not defined. That's because we probably did not run this cell. So let us start from here one more time. So I think we already set up the CARLA client. So let us do the blueprint library one more time, and then the vehicle blueprint and the vehicle setup, and then this particular cell. So now the error goes away, and we see that we have set up the camera, but we need to see the view of the camera. So let us first set the vehicle on autopilot. So this should enable the vehicle to drive autonomously throughout the route. And then if we go down, again, we have to run this cell where we created the callback function for camera, basically rendering the image to a CV2 window. And as soon as we run this cell, so this window pops up and we see that the vehicle is moving, and we are basically looking at the back or rear side of the vehicle. We are capturing uh, this this video while the vehicle is moving in the front, right? So this is how we can set up the rear view camera. And if you want to change it to a side view camera, that can also be done. So basically what you do is you'll change the rotation or the yaw parameter of the CARLA dot rotation method to maybe 45 degree or negative 45 degree and so on. And depending on at what angle you want to look at, so say for example, you want the rear view camera to act like a rear view window or rear view mirror. Like when you check the rear view mirror, you're basically trying to see what vehicles are occupying the lanes that is toward the left or the right side of your vehicle, or if there is a vehicle in the blind spot of your vehicle. So you can set up the camera angle like that so that you can have the right orientation for the camera to look at in the surrounding lanes. All right, so on this window, I'm placing my cursor on this window, clicking on it, and then I'm pressing Q, and that will basically destroy the CV2 window. And so, any question on this solution or any particular, do you want to share your thoughts? How would you have done differently, or if you have any other way of doing it? Any questions for the first challenge? I don't see any questions in the chat as well. So moving on to the second challenge that we gave you, the second challenge was, can you design a controller for the longitudinal motion of the vehicle? So in the morning session, we showed you how to set up a PID controller that was controlling the longitudinal motion of the vehicle, right? So to track a particular speed or reference speed or a target speed, whichever you call it. And so this was the function that this was the class that we used for the PID controller, uh, and we would have to manually set up the proportional integral and the derivative gains for the controller, right? But the challenge I gave you was, can you handcraft a controller yourself without using this kind of pre-built controllers? Can you design something on your own so that you are trying to track a given speed or a reference speed meaning that when you are operating your vehicle, if you want to reach a certain speed from a lower speed than that, what you would do is you would press hard on the accelerator or the gas pedal, right, or the throttle, and that will basically increase your speed over time, until a point when you see that okay, you are very close to the speed that you want to keep. So if you want to keep 40 mile per hour speed on your vehicle, when you are close to 35 mile per hour or 36 mile per hour, then you go gentle on the gas pedal, right? You're trying to slow down so that you do not cross 40 mile per hour by a large margin. So if you are over 40 mile per hour, what you do, you'd probably take your foot off the gas or the throttle, and then place your foot on the brake pedal, right? And then you gently press the brake to be able to slow down the vehicle a little bit until you reach the desired speed of 40 mile per hour. So if you think about the logic, then we should be able to design or handcraft a controller ourselves to be able to operate the vehicle longitudinally to track a particular or given speed. And that's exactly what we are going to do for the second challenge. But before we run or show the script how we do that, let me one more time, let me restart the kernel. And once we have restarted the kernel, I want to make sure, okay, let us first import the packages. So we have imported the packages, and before we move on to the next couple of steps, I want to make sure that there are no remaining vehicles or sensors from our previous setup, right? So I'm going to run these two pieces of for loops to make sure that we have taken out all the vehicles or sensors that we deployed earlier in this map. And this piece of code is going to take care of that. All right, so we made sure that we have taken out the vehicles that we created or the sensors. And then we are basically going to, again, find a set of spawn points where we can actually place the vehicles or the sensors. And then we're going to look up the vehicle blueprint that we want to use. And then we're going to try spawn the vehicle on the desired location. So this piece of code is going to take care of that. And because we are not going to do it this time using the PID controller, so we don't need to run this fill. However, this particular function, it converts the speed from mile per second to mile per hour. So let us run this part of the function, this particular function, because we'll need that anyway. So I'm going to put this function in a new cell, and I'm going to execute this cell. So now we have the get speed mile per hour function ready. And then for the vehicle, we would like to track the vehicle while it is driving on the road. So we have this function that we created earlier in the morning section to follow the vehicle position. So while the vehicle is moving along the route, we are going to move the spectator view uh, along with the vehicle so that we can see the vehicle all the time. And as soon as I run this cell, you see that our spectator view has changed, and we are just right behind the vehicle right now. So this is our vehicle that's going to be operated. And as the vehicle will move along the route, we will trace it with this spectator view. We'll chase the vehicle. All right, and then this is basically setting up the camera. So we want to see the camera view of the vehicle, and we will have a CV2 window just like before, where we will show the target speed and the current speed of the vehicle. So we are keeping this cell and executing it. And then this cell was what we did before with the PID controller to track the vehicle's longitudinal motion to track a particular speed, right? So here, if we go inside this infinite loop, we see that so basically the PID controller was giving us the control input, and from there we were applying some threshold, some maximum and minimum threshold on the controller input to set the right value or the desired value for throttle and brake. And then we were just giving those two values to the vehicle by using the apply control method inside the vehicle instance. And then we were using the CARLA.vehicle control method to assign the throttle value, the steering value, and the brake value. So right now, what we need to do is basically replace these few lines, these 3 lines of code with our handcrafted controller. and the rest of the code should remain as is. Here's a little part where we have the PID controller set up, so we can also take this part out. So I have already put it here for our reference, but before I explain how I did the handcrafted controller, let me show an illustration so that I can better explain how it works. All right. So this is a rule-based system for a longitudinal control. So let me explain what this figure means. So basically, this axis we are observing here is the error axis, meaning what is the deviation of the current speed of the vehicle from the target speed. So basically, this axis represents the speed error, which we represent by E here in our code. And E basically is the difference between the target speed and the current speed of the vehicle. So the target mph is the target speed that we want to track in mile per hour, and the speed mph is the current speed of our vehicle in mile per hour. And you can see from this equation, if your target speed is higher than your current speed, then your E is going to be positive, right? So this is the positive axis. And when your current speed exceeds the target speed, you will basically get a negative error. So that's why we have the negative axis here. Now we have divided this window into 1, 2, 3, 4, 5 bands. So the middle band here, which is between the minus deadband to plus deadband, is basically where your errors are very low. So maybe you are very close to your target speed. You are within maybe plus or minus 5 mile per hour within your target speed, or you can choose you can choose how to set up your deadband. You can play along with the numbers to see what values work the best. But that's the window where we are very close to the target speed. So what should be our action in that case? So we will, if we are over the speed that we are targeting to achieve, that means that our error is negative. In that case, we'd have to put some brake, right? A very gentle brake. If we see that we are a little bit we are a little bit lower than our target speed, that means our error is still positive. So we have to be very gentle with the throttle because we are very close to the target speed. But if that is not the case, if we are within this band between the dead band and the big error window, where we are maybe 4, 5, 6 mile per hour off from our target speed, in that case, we'd have to go with the throttle. We would have to place a little more gas in the throttle, right? In the opposite end, if we are within this opposite window where we are between the deadband, minus deadband, and the minus big error, that means we are quite far off, quite past of the speed limit that we are targeting, or the speed we are targeting. Maybe we are almost over 5 mile per hour, the speed limit. So say the speed limit is 40 mile per hour, we are maybe operating at 45 mile per hour. Then we'd have to brake a little bit harder than we did for this band. And then the far right and the far left side of this figure is when you have a very big error, right? So you're very off from your target speed. In that case, you would have to throttle hard if you are lower than the target speed. And if you are going very fast, in that case, you would have to brake hard to be able to make sure that you are closing in the gap. All right, so this is the logic behind our crude controller that we designed here. So as you can see, we replaced the PID controller portion with this few lines of code, where basically we have a nested if loop where we are basically tracking the speed error. So if we are over the big error, so if we are here, that means that we have to pose some strong throttle or strong acceleration. And in that case, we are putting throttle to 0.6. And then if we are over the dead band, but within the big error, that means we can place a gentler throttle. So we reduce the throttle value to 0.25. And in both cases, we don't need any brake. So we put the brake value to 0. On the other end, if we are over our speed error is less than the negative big error, that means we are here in this window. That means we have to brake hard, and that's why we have a large value for the brake 0.55, or we can set a higher value if we want. And then if we are within this window where we are between the minus deadband to minus big error, then we have to press the brake softly. So we have a softer value, a smaller value for the brake. In any other condition, when we are over here, we are going too fast or too slow. In any other condition when we are within this deadband, so we are very close to the tracking speed, so we gently press the throttle. But yeah, I mean, of course, you can refine this or make this band even finer, trying to play around with the different limits or thresholds so that you can have a better control on the longitudinal controller in terms of tracking a particular speed, and that's definitely doable as well. All right, so let's see how this operates on our vehicle. So I'm going to close down this window. So we already run up to this cell.
So,
This
Sabir,
was
there is
our
a question or comment in the chat box. You have addressed that, right?
yes. Yep.
Thank you.
Yep. All right, so let's run this cell now. So as soon as I'm going to run this cell, you'll see a window will pop up where we will be able to see the camera view of the vehicle that we have set up. So if we press Shift Enter, you see that this window popped up where we see the target speed is 15 miles per hour. The current speed is 11 miles per hour. And because we did not pose any steering condition where the vehicle had no knowledge of when to stop or whether there is an obstacle in front of it, it crashed right into the museum pathway. So we see that it just crashed there, and the vehicle is on stall. So the speed is right now 0 miles per hour because we cannot break through this obstacle, right? So that's how it works. So let's look at it one more time because it was very fast. So I'm gonna press Q, and that's gonna take up. Okay, well, I would have to rerun the server to be able to run it again. All right. Yeah, I think my server just crashed for some reason. But anyway, so that's how we would design a handcrafted controller to control the longitudinal motion of the vehicle. And if you have a better idea to control the vehicle longitudinally using some handcrafted controller, please feel free to unmute yourself and show us your solutions. So that would be a very good opportunity for us to explore different options as well. Any questions or any comments or any concerns? Okay, if no questions regarding the challenges that we gave you, overall, if there's any issue that I can help you address, so please feel free to unmute yourself and let me know if there's an issue that you would like us to discuss, or anything you would like to know more about CARLA. We can try to help you with that as well.
Well, I have a question.
Yes, please go ahead.
So before we were looking to the LiDAR data, and we saw that LiDAR always shows up like a angle range while rotating. So like when LiDAR rotates, you can see like 30 degrees, 50 degrees of range at each frame that the LiDAR captures. But like, let me show my screen with you. For example, I have access to this LiDAR Oyster, and after that you have, we can see like the whole 300 degrees of the LiDAR at once. That is different than like the one that you showed up, that you can see everything at the same frame. I don't know. I suppose there is like how we can see everything at once, or like how people that work with CARLA, how they visualize like that, or like it's just like in a smaller angle per frame of the data capture?
That's actually a very good question. So the type of LiDAR we use is a raycast LiDAR. And I have to check in the CARLA documentation to see if we can set up a particular angle. But I'm pretty sure there will be a way to set up a particular angle for your ray, the laser that you are pointing with from your LiDAR sensor. Um, but one interesting thing is when we saw the LiDAR window, so we basically have a flat view, right? But if you play around with your mouse cursor and your keyboard, you'll be able to set up a different angle where you are looking at the LiDAR from a different point of view. But I'm not sure if that will resolve the issue of like the one that you are trying to say is that whether it is just pointing one ray around or whether it has a field of view that is wide enough to cover like a certain height, right? So I'd have to check with the documentation to see how to do that.
Okay.
But
Thank
if
you.
you go to the documentation, so let me share my screen one more time
Okay,
and
let me.
see if we can find out. So let us look for LiDAR. So we see that there are one and two. There are two types of LiDAR. One is the raycast and another one is the raycast semantic. So my assumption is this is for semantic segmentation, and this is for the regular LiDAR operation. So if we look at the attributes, let us see if we can find out a way. So channel, drop of general red, intensity lumen, zero intensity horizontal, FOV, lower FOV, rotation frequency. I see. I see. So these are the two parameters, I believe. One is the lower field of view, another one is the upper field of view that you need to play around with to be able to set up the field of view of your LiDAR. So I would say try with different values for these two particular attributes and see like how much of a view you can open up for the LiDAR.
Okay.
Thank you. Any other questions from Matthias or others? Okay, if not, then I think we are very close to our finish time. So we were supposed to end at 3:30. If no other questions, then I think we are going to end the session today. But please feel
I have
free to
one more
reach.
question.
Oh, yeah,
Sorry.
please go ahead,
Uh,
Matthias.
just like I saw that the last release of CARLA was the 9.16. I don't know if I'm right, but they also released some time ago the CARLA 10, was
Yep.
0.10. That's with Unreal Engine 5.
Mhm.
I don't know if you know, like there's people already using the new version of CARLA with the new Unreal Engine, or people are keeping using with the one with the other Unreal Engine. Uh, I don't know. I don't know a lot of people that work with it that I would like to understand, like when to use one, when to use the other. Like I don't know which one is the best because the Real Engine 5 it's more modern and more updated. And there's more features. For example, if you want to use build from source, Carla.
Well, to answer your question, yes, you're right. The latest version of, I mean, if you go to the Carla website, it shows you the latest version is the 0.9.16. And the version that you were talking about, 0.10, which they released in 2024, I believe, end of 2024, it is built on the Unreal Engine 5.5, and it has some more capabilities than the current version of Carla, which is the most stable version, 0.9.16, the one that we use today. Uh, but I think when they release a version, there are typically a lot of bugs and issues that they have to go back and forth to be able to resolve. And that's why they're not advertising 0.10 as the latest stable version on their webpage yet. But I think in the future, or in the near future, when they feel like okay, the 0.10 version is ready for use, they will place that on their on their front webpage that this is the most recent version. So that's one reason. The other reason I did not want to utilize the 0.10 version for today's workshop is that if you look for documentation, you will see that the 0.9.16 has a very detailed documentation, but the 0.10 version, I felt that the documentation is still not as comprehensive as the stable version. And also, if you want to look for tutorials, you will see that there are many different tutorials available for 0.9.16 on YouTube, on blogs as well, but not so much on the 0.10 version. So because this is the most stable version, mostly utilized, so that's the one we chose for the workshop.
Okay.
But yeah, feel free to work with the latest version as well on Unreal Engine 5.5.
Thank you.
Thank you, Matthews. Any other questions from anyone? Okay, so if not, then just two more things I wanted to mention before we close out. So we have been recording this entire session today, and I'm gonna stop the recording as soon as we end the meeting. And once the recording is available, I will share it with Dr. Ali Karimuddini and Christina, and I believe they will be able to share with all the attendees of our session today. So that's the first thing. The second thing is if you have any more questions regarding today's session or regarding CARLA, because I mean that's the best way to learn from each other through this workshop, that we are facing some challenges and we help each other to resolve those issues. So that's the best way to learn for me as well. So please feel free to send me emails at msalik@clemson.edu anytime if you have any questions regarding CARLA, and we can catch up from there. Thank you. Thank you all. Thank you, Dr. Chaudhary.